He the cat was logical, imperturbable, and had pointed ears, and that's in the citation.
Nice.
And there aren't there like over 10,000 named asteroids now?
And Wendy has just come out with the asteroid named for Ulasti, which was named for Gene Mueller's cat. And that's a very nice asteroid name that they have.
And Mike Wiesner's the first one to log on. He says, hello from thunder showery southern Arizona.
Mm.
Yeah, you might want to send some of those thunder showers down this way. And Wendy reports we've had 8 drops today.
It was quite an episode yesterday with having Facebook shut down.
Yeah.
Yeah.
And Instagram and what else? WhatsApp and their whole universe shut down.
Did you see the comedic memes where people were in despair and staring around and finally either picked up a book and smiled, starting to read a book, or they ran outside, kids ran outside and actually started to play with each other again.
Wow. Yeah.
Looked like the 1970s.
Yeah.
Yeah.
Yeah, it sure did. It surely did.
Goodness, we already have 100 messages.
Wow.
That's pretty fast.
Do we have time to say hello to each one of them?
Yes. Hello, everyone.
Hello, each one. Hello, each one. How are you?
You have to say it 100 times.
Yeah.
Yeah. We have Tarek watching from the UAE. Norm Hughes is watching. Who else? Of course, we know Mike Wiesner's watching.
And Wendy's
Sentil
watching.
Nagapan is watching.
Yep, she's listening.
Anyways, greetings, everybody. And they're saying hello back. There we measure shadows and we search among ghostly errors of measurement for landmarks that are scarcely more substantial. Yeah, I imagine that Hubble really just kind of, lost it at some point, on some nights, cold, looking at, ghostly images on the, his negatives, his glass plates.
Well, and just to be fair and forthright with everyone, he wasn't always the most popular guy on the block, with his associates. He was a little gruff. It didn't take him much to be cranky sometimes.
I see.
Absolutely. You sure hit that nail on the head, David.
We love what he did and we love his importance, but he was a little crabby.
Crabby.
Edwin Hubble. Yep.
So at Mount Wilson at the monastery, I'm sure I'm sure several of you have been there. But in the room where it's kind of like the living room, and then you go into the dining area where they would all dine, Hubble would make sure he was the first one there. And then what he would do is he would go to the encyclopedia, open it up quickly at random, look at a page, read that page, okay, and then basically occupy the majority of the conversation that night talking about this subject. Giving the impression he was one of the most well-read men in the world.
That's kind of clever, actually.
There you go.
Mm.
Okay.
Less than a century ago, the bright arc of our Milky Way was thought to contain all the stars in the universe. But astronomers were perplexed by a cigar-shaped object in the autumn sky called the Andromeda Nebula. Some astronomers thought it was another galaxy like our Milky Way. It too had a flattened disk shape. But how far away was it? In the early 1920s, astronomer Edwin Hubble photographed the nebula in detail. He found a pulsating star hidden deep in one of its spiral arms. Edwin Hubble used it to calculate the distance to the Andromeda Nebula. This showed it was far beyond our Milky Way. Andromeda, in fact, was really a separate galaxy. The Hubble Space Telescope has recently observed this star as a tribute to the landmark discovery.
Well, hello, everybody. Welcome to the 66th Global Star Party. This is a very special, auspicious day because this is the day that Edwin P. Hubble discovered a Cepheid Variable Star in what was called the Andromeda Nebula. Of course, that was, in fact, a star in a separate island of stars, which we now know as M31, the Andromeda Galaxy. But up until 1923, I think that the universe was much smaller in most physicists' minds and astronomers' minds and science, accepted science of the day. And overnight, that expansion was, into the millions of light years. And of course, as that got refined over the years, of which I believe we're still refining, we have now discovered that the universe is far larger than ever previously imagined. I think that it's important to remember this day because, what this shows is the process of science. We have hypotheses, we create theories, we create experiments, we carry out those experiments to try to prove or disprove those theories. And when they are disproven, scientists that have maybe held on to the old ideas for a lifetime have to disregard them and start all over again. That's easier said than done for a lot of people. And but that is the process of science. And it is one way to try to understand the nature of reality. And so it's something that a lot of people don't understand. Basically, this process. So there are sometimes no hard facts, that you can hang on to forever, because all it takes sometimes is one observation and it can really rock the boat, as it happened in 1923. So, we will start our program with David Levy, who always brings poetry and a certain feeling to every global star party. In fact, every event that he does, and he talks to you from the heart, but he also talks to you from, the written words sometimes of long, long ago that still inspire and capture the feeling and understanding of what we're trying to understand now. And as I've always mentioned, David is a friend to us all, definitely a dear, close friend to many of us here on the Global Star Party. And so again, I want to thank David and David, the two Davids that are on here right now, for being on Global Star Party so many times. But right now, we'll turn it over to David Levy.
Well, thank you, Scott, and I'd like to add my welcome to all of you. While we were waiting, we were having the pre-session rehearsal, and you guys wouldn't be interested in that because you'll have to talk in ancient Greek when we do this. Anyway, we were talking about Hubble, and people were saying how wonderful Hubble was, Saint Hubble. And then David came up to something, and he said something that I found interesting. He said that Hubble might have done a lot of things, but he was not an angel, and he had a lot of enemies in his lifetime. And to that, I could add that, I found that out while I was writing the biography of Bart Bok, the man who saw the Milky Way. It was published 1,000 years ago by the University of Arizona Press. It seems like 1,000 years ago. Well, one of the things that Bart told me, that Hubble went to Oxford for a while, and he came back talking like he had a hot potato in his mouth. And so this was a very interesting thing. And of course, Bart was a protege and a very good friend of Harlow Shapley. And Shapley and Hubble never did get along very well. And so someday we could actually go into some of those details. But now we have the Hubble Space Telescope, and it is time for my quote of the week. We're talking about cosmic beacons this time. And we're talking about Hubble and his discoveries and the work that he did by showing the expansion of the universe and how wonderful that was. And that brings me back to my favorite writer, Shakespeare, and his play Julius Caesar, because he was looking at cosmic beacons in a different sense. In those days, you couldn't look for other galaxies. Everything that you had, this was in the days before the telescope, just before the telescope. And in those days, you were looking at things in the sky, not that far from the Earth. For example, comets. And so my quote today is going to be something that Shakespeare wrote in Julius Caesar. He had Calpurnius Caesar say these words, probably about the comet of 1599, which appeared, I believe, the same year that Julius Caesar was written. And it goes like this, very simple. When beggars die, there are no comets seen. The heavens themselves blaze forth the death of princes. Thank you, and back to you, Scott.
Well, thank you very much, David. That's awesome. Up next is Carol Orge. Carol is the president of the Astronomical League. Carol, I can't remember how many times the Astronomical League has been on Global Star Party and other programs now, but it's got to be approaching maybe
probably 30-ish or 40. I don't
well,
know.
I think more than that. I think it's
probably
at least 50 times.
50, 55, something like that. Yeah.
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 So,
we've been thrilled to have the Alliance service. That's been very nice.
Yeah, it's been great. So I love the background behind you with the Milky Way and
That's in my backyard, not.
Is it really? How do you get the lighting just right? It's amazing, so, but that's wonderful. If you guys don't already know it, the Astronomical League is the world's largest federation of astronomy clubs. It has tens of thousands of members, and they have an at-large membership program that's open to anyone in the world. So they have probably the most vast collection of observing programs that you can get involved with, everything from outreach to, variable stars to you name it.
Approaching 80.
80 programs. There's no other organization that has that much to offer to Astronomy Club members. They have every year, they have the Astronomical League convention where you can see luminaries of astronomy give talks. You can hang out with your peers. It's just an amazing event. Where is the next one going to occur,
The
Carol?
next one will be in July of 2022 in Albuquerque.
In
We've
Albuquerque.
tried it 3 times and we're finally going to make it this time, I believe.
I believe
They've
you
been
are
very
too.
patient.
I
The
believe
local
you are
people
too.
have been.
Excellent. So I'll let you get started, Carol, but thank you very much for coming on.
Speaking of Edwin Hubble, I would like to say that he spent all of his youth in my home state of Missouri. That wouldn't quite be true, however, because before he was 1 year old, his family moved to Illinois. So he was a very much of a short tire, but I really like to claim that he's a native, at least in a certain type of way. Okay, why don't I share my screen and let's go with some questions.
Sure.
Okay, we'd like to get this warning in case one of the prizes you win during the month is an instrument, telescope, binoculars, anything that's going to be looking at the sun. We want to make sure the proper filtering is there. So that's our credit there. And now let's jump right into the answers from GSP 65, which was the last one. The first question, this is the closest star to the sun. Which of the following does not accurately describe it? It has a planet. It's a red dwarf star. It's 25 billion miles away, or it orbits 2 other sun-like objects, sun-like stars. And the C is the one that's not correct. It's actually 25 trillion miles away, a slight difference.
Slight difference, yes.
Number 2, when the moon is at first or last quarter, tides on the Earth are at their smallest. What are these tides called? Neap tides, spring tides, diurnal slide tides, or ebb tides? And the answer is A, neap tides. And everybody had that on the tip of your tongue, right? Okay. Number 3, John Glenn was the first American to orbit the Earth. What rocket propelled him into the orbit? Was it the Redstone, Jupiter C, Vanguard, or Atlas? And the answer is Atlas. Okay. And the correct answers from that star party held on September 28th are Teresa Bippert Plymate, Andrew Corkle, Andrew's on here quite often, Israel Mataroso, who's also on quite often, and Cameron Gillis, another charter member of this group. So 3 out of 4, that's pretty good, isn't it?
Yes, we need more people to participate in these. And so you can send your answers to secretary@astroleague.org. And
now let's get to the ones for tonight.
yeah.
Question number 1. What is the name of the new AL Imaging Award for Women, sponsored by Explore Scientific? What is the name of the new AL Imaging Award for Women, sponsored by Explore Scientific? And again, send your answers to secretary@astroleague.org. Question number 2. Ariel, Umbriel, Miranda, Titania, and Oberon are all moons of which planet? Ariel, Umbriel, Miranda, Titania, and Oberon are all moons of which planet? Number 3, what unit of length is equal to about 3.26 light years? What unit of length is equal to about 3.26 light years? And again, send your answers to secretary@astroleague.org. And this is the month for spooks. So Astronomical League Live will feature all kinds of goblins for that event, including Barbara Harris. And of course, David Levy will be on there as well. Molly Wakeling, John Goss, Terry will be there. And Mary Stuart Adams will talk about passing between the worlds under October skies. So make sure you join that. And the date for that.
And don't forget yourself, Carol. You're on there too.
Well, yeah, we threw me in there too. And so that will be the next one, and October 15th. So a little over a week from now. So mark that on your calendar. It should be fun. And now back to you, Scott.
Okay, well, thank you very much. Coming up next is David Eicher. David has written many books, but one of his books that I'm very fascinated with is his Galaxies book. Not only are there amazing photographs in it, but explanations about the latest findings and understandings of galaxies and the way they work, how they're formed, and where, what will be their demise. So David, I'm going to turn this over to you now. Normally we give short lectures, but this is the whole enchilada. Okay, this is if you would go to one of the big star parties, you would hear a lecture of this length, and so we thought it would. David Eicher and I thought this would be very appropriate on this particular day. I'll turn it over to you, David.
Scott, I promise not to talk about all 100 billion galaxies, though. That would be even longer.
And galaxy
but I will
954 billion 729,252 is.
That would be a little too much. But I will share my screen. Can you see a slideshow?
Yes.
Good. Excellent. Well, we thought that Scott and I thought on this anniversary night of Edwin Hubble's that galaxies would be an appropriate thing to talk about, because really we've learned so much just in the last 10 or 15 years. We're in the midst of a revolution of knowledge in astronomy. And we've only known about the nature of galaxies now. Tonight, the anniversary will be 98 years ago that Hubble identified this very special plate with the Andromeda Nebula, as it was called at the time. So we thought we'd talk a little bit about this tonight and a little bit of background about galaxies, because there really has been a revolution in the last 10 to 15 years about what we know on these star systems and how they were formed and how they evolve and what will be their fate. So it all began, as we've talked a little bit already tonight, on October 4th, 1923, when Edwin Hubble, who was a young, very ambitious astronomer, trekked up to his favorite telescope up above his office in Pasadena, up to Mount Wilson. And at the time, the largest telescope in the world was the 100-inch Hooker telescope. It had taken over the title just around the time of World War I from the telescope that was built by Lord Rosse as an amateur in rural Ireland, of all things, more than half a century earlier. So really, astronomy at this time was getting into the first phase of true astrophysics and studying these objects in an analytical way. So at the time, it was a very different world culturally, and the setting that Hubble was in as well. He was in a Los Angeles that had about 1 million people, a population at Caltech. Across town, Robert Millikan had just won the Nobel Prize in physics for measuring the charge carried by a single electron and for the photoelectric effect. Across town, a young Amelia Earhart was taking flying lessons, and a cartoonist, Walt Disney, arrived in town with $40 in his pocket. So it was a very different kind of Los Angeles than what we know now. Hubble was very interested, of course, in studying his favorite kinds of objects, spiral nebulae. And as we talked a little bit about as we were warming up, and David mentioned as well, David mentioned, Hubble was not an easy guy to get along with for his colleagues. He was a little brusque and quite a lot of self-confidence, shall we say, he always showed. But he was very focused on these spiral nebulae, his favorite kinds of objects that a number of people here and there were focused on studying, and nobody really knew what their nature was at the time. He was taking a plate on the evening of October 4th at Mount Wilson Observatory of his favorite object, the spiral nebula in Andromeda, M31. And at the time, of course, most everyone thought these nebulae were within our galaxy, and there was only a vague idea of the sort of what we now call the cosmic distance scale of the size of the universe and the things around us. Hard stuff to figure out when you're trying to sort of derive all this stuff for the first time. Hubble was very excited, of course, and so he took by studying this nebula, and he recorded what he thought was a nova, and so he took a second plate the next night, and that was the evening of October 5th, 98 years ago tonight. He studied this object very carefully, and you can see near the top of this very famous plate called H553H, he labeled a star with tick marks, N for nova. He thought it was an exploding star in this galaxy, perhaps. He compared it then to a number of other earlier plates and of other kinds of objects, and he practically fell out of his chair in his Pasadena office because he recognized a very implicit pattern of brightness variation in this star. This star was a so-called Cepheid variable, of course, as we know now, named after Delta Cephei, the prototype. It has a very clear, distinct pattern of brightening and dimming over a particular period, and its intrinsic brightness, its absolute brightness, is known very well as kind of a star. And he was stunned because this Cepheid variable was so incredibly faint that was in this nebula. So you can use that because the absolute brightness is known very well as a gauge of distance. So Hubble was stunned, realizing, you can see he crossed out the N and wrote var for variable star here in red ink on the plate, the glass plate. And he was stunned. He couldn't believe, he was in disbelief, because by his estimation, that meant that this spiral nebula was 1 million light years away. Now, at the time, most all astronomers believed the entire universe, all of the cosmos, all of creation, was only a third of that size. So this seemed like a ludicrous, a ridiculous discovery. Of course, now we know that the distance to what became the Andromeda galaxy is 2.5 million light years. So Hubble knew it was large, but even he underestimated it at the time. So in a single observation, Edwin Hubble, despite his brusque personality and ambition, he reset the cosmic distance scale, and he really deciphered the nature of galaxies in a single observation. This was one of the incredible milestones, this glass plate of the history of science. Well, research by Hubble and others like V.M. Slipher at Lowell Observatory determined the universe was expanding. Slipher actually had used a spectrograph, which you can see at the Collection Center at Lowell in Flagstaff, a decade before Hubble's discovery, to see that these spiral nebulae, most all of them were receding away from each other. And therefore, if you reverse time, in the equation, the conclusion is that there was a point of origin from which the universe began. So the expanding universe, the nature of galaxies, the cosmic distance scale of this universe being very, very large, which there had been a famous argument in Washington over a few years before, was suddenly seemingly resolved. Tracing this whole motion backwards, of course, meant that there was this point of origin, which later came to be called the Big Bang, and now we know is 13.8 billion years ago. Well, as with all sciences, the early days of galaxy research consisted primarily of classification, whether it's butterflies or animal bones or minerals or what have you. Before you really understand what's going on with objects as a scientist, you need to classify them and sort them and work out the different types of them in meticulous detail. Hubble worked a lot on this problem early on, and he came up in the 1930s with a classification scheme that most all of us, at least us older astronomy enthusiasts, are familiar with still, this tuning fork diagram of the kinds of galaxies, spiral galaxies, barred spiral galaxies that have spiral arms, but have a prominent bar through the center of the galaxy from which the arms emanate. Or elliptical galaxies, big spheres of stars. Those basic types he recognized, and he wrote about these in a famous book and defined them called The Realm of the Nebulae, which he published in 1936. So for a long time after this discovery, this era of classification, of understanding the properties and types of galaxies went on. Later classifications added a lot of types to this understanding of the kinds of galaxies and what they are, and therefore some clues to their evolution. And a fellow that I got to know, had the fortune of knowing, and I think others of us here as well, near the end of his life, the French astronomer Gerard de Vaucouleurs, who went over to Texas and was at Austin for most of his career, in the late 1950s and early 1960s, developed a much more sophisticated classification scheme that's sort of a 3D oval that we call the cosmic lemon sometimes now, that talks about the details of the bars of galaxies, whether a galaxy has rings of encircling matter, how tightly or loosely wound the arms are, and all sorts of other details. And he also added a lot to our knowledge of some strange types of galaxies, like irregular galaxies that seem to be big disorganized masses without much form, or peculiar galaxies that seem to be erupting or colliding or in all sorts of chaos. So the Hubble first worked on this a lot, and then the de Vaucouleurs scheme is still the galaxy classification scheme that we use today. Well, by the mid-20th century, astronomers realized that galaxies are the basic building blocks, large-scale building blocks of matter in the universe. Their stars, gas, and dust contain most of the visible matter that we know of. For years, astronomers estimated the number of galaxies at about 100 billion. You may have seen a couple of years ago, a pal of ours, a few years ago now, in 2016, an astronomer named Chris Consolis, who's in England now, published a study that caught wind of a lot of people's attention and said that maybe there are 1 to 2 trillion galaxies in the universe. But remember that, of course, as we know, that telescopes are time machines. As we look farther away, looking back in time in the universe. And long story short, in an argument that really spiked up in the 1940s, 50s about how galaxies form, it's now clear from Hubble and from other things, and the Hubble, the telescope, that galaxies form as small objects that come together by gravity and merge into larger objects. So long ago, maybe we had a couple trillion little proto-galaxies. Now in the current, if you will, modern age of the universe where we are now, there's something more like 100 billion, a paltry 100 billion galaxies. Closer galaxies to us, of course, as we know here, as closer to how they are in cosmic time as we're talking together tonight. Well, where do we start with understanding galaxies? For some of us who were lucky and others of us who live in Wisconsin, and we can only do this once in a while, we can wander out into a dark sky and see the Milky Way, the band of the Milky Way, overhead at certain times of the night each time of the year. And of course, it's the unresolved light, the band of light from our galaxy's disk seen from within. And deciphering the structure of the Milky Way took a long, long time because it's hard to map a galaxy when you're inside it. We don't have any images of our Milky Way, of course, from the outside because it's really big and the distances are large. But on any dark night, you can see the band of light. If you're in a really dark sky, you can see lots of detail within the Milky Way, like these dust clouds along the disk and other features, of course, as well. We now think that the Milky Way contains something on the order of maybe about 400 billion stars. The number is not very well precisely known, though, because the most abundant kinds of stars are M dwarfs, are faint red dwarf stars, and they're hard to see over long distances. They're much more abundant, the smaller, fainter, low mass stars than even middleweight stars like our sun. We'll talk a little bit later, I think a tad more about this, but the Milky Way is a barred spiral for most of the last century since the discovery of the Andromeda galaxy's nature. We thought our galaxy was also a simple spiral galaxy with spiral arms. But relatively recently, we discovered that it's a barred spiral, and we now know what the barred arms and spurs of our galaxy look like pretty well. And fortunately, our sun and our solar system are out in what's called the Orion arm or the Orion spur, which is about 26,000 light years out from the center of our galaxy. Our galaxy's disk is at least 100,000 light years across, end to end. And so we're just a little bit more than halfway out on one side of our disk, which is a good thing because closer to the centers of galaxies, even relatively well-behaved galaxies like the Milky Way, you can run into all sorts of trouble, which we'll talk about as well a little bit more in a moment here. So this is an infrared image looking toward the center of our galaxy, and you observers probably know this already, but I'll mention it again. If you go out and look toward the constellation Sagittarius and look between the open cluster M7 and the Lagoon Nebula, if you draw a line between those two objects, about midway, the midpoint of that line is essentially the direction of the center of the Milky Way. Of course, we can't see, though, anywhere near toward the center of our galaxy because there's so much obscuring dust in the way. We can see with our eyes and even with our best telescopes, typically invisible light about a quarter of the way toward the middle of our galaxy here, for the most part. Our galaxy does contain a supermassive black hole with a mass of about 4.3 million suns of our sun's mass, which is not a super heavyweight black hole, but it is a black hole in the center of our galaxy. Other hazards, as I mentioned, as well in the active, busy, dense centers of galaxies like antimatter and like high energy radiation, frequent supernovae, exploding stars, and other hazards. So it's a good thing that we're out in the calm countryside, if you will. Well, this is the Andromeda Galaxy, Tony Hallis's modern image of it, which is beautiful. And like people, galaxies like to hang out in groups when they're not in a pandemic, some containing more than others. Our group of galaxies is called the local group of galaxies. It was named so by Hubble in his book, The Realm of the Nebulae. And we have at least 55 galaxies in the local group. But you can see evidence of what's going on with some of these small galaxies, even in this image. The two dwarfs here, M32, which is just above the disk there, and NGC 205, just below the disk of the main galaxy there, you can see that the halo of NGC 205 is warped there, and that's tidal disruption that's causing that galaxy to be distorted from the mass of the main galaxy, the Andromeda galaxy there. And what larger galaxies tend to do to small ones that are near them is to eat them. over time and absorb them. We know the Milky Way has done this. We know that there's a small dwarf galaxy called Sagdig that's happening to right now, that the Milky Way is beginning to shred apart. And this will eventually happen to M32 and NGC 205 here. So there may be as many as 100 small galaxies in our local group, some of which are behind the disks of the larger ones and too faint to see, just like those faint stars that are hard to see over long distances. The local group contains 3 primary, pretty big galaxies. The Andromeda galaxy is the largest. The Milky Way is about 60% or 70% as large as Andromeda. And then the third galaxy, big galaxy in our group, is the Triangulum galaxy, M33, sometimes called the pinwheel. And you can see it here. It's very well known for having a large number of star-forming regions in it. You can see these pink so-called H2 regions of doubly ionized hydrogen. The big one that is above and to the right of the center of the galaxy is so large it has its own NGC number. It's called NGC 604 and is one of the 2 largest star-forming regions known in the universe. It's enormous. The Triangulum galaxy is about 3 million light years away compared to Andromeda's 2.5 million. And it is the third of the major spirals. Although they exist in groups, there's an enormous space, usually, between these large galaxies that separates them. But not always. Funny things can happen in the emptiness of space. And although galaxies, as I mentioned early on, are generally all receding from each other as the universe is expanding and as dark energy is even accelerating the expansion of the universe, but gravity works on smaller scales as well, of course. And so a lot of galaxies that are near each other, especially in clusters, rich clusters of galaxies, collide and they merge. And so here's a good example of that. Fortunately, we can see a lot of these with our telescopes from the backyard, like the great telescopes that Scott is providing for us. This is the antennae, NGC 40, 38, and 9 in Corvus. And there are many, many examples of this in the sky that you can see in a smaller or moderate telescope. You can see the disruption, I think it's fair to say, in the centers of these 2 galaxies that are coming together and merging, and how the nuclei of these galaxies will eventually merge and become a supergalaxy. Here's another example, NGC 2623, of merging galaxies a little bit farther down the road. It's not a terrible thing, this kind of chaos in a galaxy. It's simply what galaxies do. Our own Milky Way, we believe the disk of the Milky Way formed about 9 billion years ago as an ordinary disk galaxy. It contained perhaps as many as 100 tiny proto-galaxies that long ago in the history of the universe that came together and formed this disk. And we'll get to that a little bit more in another image here shortly. And we now know, because of our friends at Harvard, Avi Loeb and his collaborators, that one day, something on the order of about 5 billion years from now, the Milky Way and Andromeda will actually merge. The Andromeda galaxy is coming toward us at about 320 kilometers per second. And although it's a long way off, 5 billion years from now, it will hit us right in the face. We'll have a merger and we'll have a big super galaxy that Avi likes to call Milkomeda. As we move farther out into the universe, we encounter larger structures of galaxies. Of course, this is the core of the Virgo cluster, which is the nearest large group of galaxies near us. It contains about 1,300 galaxies of all types, all morphological types. It's about, the center of it is about 54 million light years away. So the diameter of our local group, which I mentioned, is about 10 million light years. So 5 times that diameter of our little group is the center of this big group of galaxies that's near us, the Virgo cluster. Fortunately, dozens of bright Virgo cluster galaxies are visible in backyard telescopes of all kinds. So that's why the spring sky when in the evening when Virgo is well visible to us is a galaxy hunting paradise. The Virgo cluster contains all kinds of galaxies, disk galaxies of all kinds. And one of the largest of all nearby galaxies, M87, which is a so-called giant elliptical galaxy. Now, it's clear from what we now understand about the way galaxies form and analogously solar systems form, that typically you get a disk of material coming in gravitationally that rotates, and it angular momentum keeps it together and it forms a rotating disk. Well, the puzzle was, well, how do elliptical galaxies form that are huge spheres of stars and gas? It was a mystery for a long, long time. And now the predominant belief is that elliptical galaxies form from mergers, and that's how you get them. So M87 is a giant galaxy compared to ours, not necessarily across its belt, if you will. It's 120,000 light years across. Our Milky Way is about 100,000. However, it's a sphere rather than a flat disk of a couple thousand light years depth. So the mass is huge. It has 200 times the mass of the Milky Way galaxy. And you can see maybe here a tiny little jet to the upper right of the center of this galaxy. I don't know if you can see that on your screens. Very close into the center of this galaxy, a tiny white little jet that's very short. That's actually material that's being ejected from the central black hole of M87 here, which has a mass of about 3.5 billion solar masses. That's a black hole with a mass of about 1,000 times greater than the Milky Way's black hole. Also, you can see lots of little tiny dim fuzzy stars scattered around this field, but most all of them are not stars. They're globular star clusters, spheres of really old stars that came together and did not fall into the galaxy's center, but stayed in these balls of stars that actually formed before the disks of these galaxies. M87 has about 12,000 globular clusters compared to the Milky Way's approximately 200. Well, farther away in the universe lie much more exotic objects. Here's a spiral galaxy with a slight inclination, and you can see 4 stars around the center of this galaxy here. But what's happening here is that Albert Einstein once again is proven right. This is an example of gravitational lensing, which the theory of general relativity predicted in 1916. And what's happening here is that there's a bright quasar, and that is the enormously energetic center of a young galaxy that's exactly behind this galaxy that's much closer. And the light from the quasar is being bent around the galaxy to form 4 images here of the same object. So again, do not bet against Albert Einstein. This is one of the deepest images ever made of the universe. The Hubble Space Telescope, named after our hero of the night tonight, took a series of very deep exposures of the sky over time from early on. And this is the latest one that's one of the so-called Hubble ultra deep fields. It's a tiny, tiny piece of sky in the southern hemisphere sky. And if you hold up a finger and look at your fingernail, that piece of sky that's shown here is a tiny piece of your fingernail diameter at your arm's length. And yet you can see a couple of bright stars in this field that have diffraction spikes, but most everything in this field is a galaxy. There are 10,000 galaxies in this tiny, tiny field of sky. And this is how the estimation of 100 billion galaxies in the universe is made, is extrapolating this kind of a field over the sky. These tiny little blue galaxies, proto-galaxies that you can see in this image, that are a few hundred million light years, a few hundred million years after the Big Bang, are what came together and formed normal galaxies later on in cosmic time. Well, since the 1960s, as if astronomers didn't have enough problems, they pieced together the story of lots of high energy objects around the sky. One of the first kinds of these objects that they found were radio loud objects, the tiny little bright points that were identified in various radio catalogs, like the third Cambridge catalog. This is 3C273, an object from one of those catalogs, and they didn't understand it because it seemed to be extremely distant and yet quite bright. How could that be? The mystery deepened because Martin Schmidt at Caltech began to study these in 1963, and he named them quasi-stellar objects shortened to quasars. And then astronomers found a whole cosmic zoo of other kinds of high energy objects, B.L. Lacertae objects, Cepheid galaxies with energetic centers named after the American astronomer Carl Cepheid. Lots of other types of high energy objects that mystified astronomers at first. However, by the 1980s, astronomers began to understand that these were all the same types of objects viewed from different geometries. And it turns out that these are, again, the centers of very high energy young galaxies. And what's happening here is that black holes are powering a lot of these galaxies. The concept of black holes goes back more than 200 years to an English natural philosopher named John Mitchell, who came up with the idea, the concept of dark stars that have such a strong gravitational pull that nothing, not even light, can escape them. But there was no evidence for black holes until 1990. But really in 1975, two famous astronomers, two pals of ours, one of whom is still here and one of whom is sadly gone now, Stephen Hawking and Kip Thorne, made a famous bet that one of the first stellar black hole would turn out to be a black hole. And famously, Hawking lost the bet and had to get a magazine subscription sent to his friend Kip Thorne, which was Penthouse magazine. But anyway, the long and short of it, if you will, is that by 1990, it was clear that black holes actually existed after more than 200 years. And soon thereafter, a few research teams, chiefly John Cormandy, who was also at Texas, and Lewis Ho and their collaborators started finding lots of black holes, evidence for lots of black holes in the centers of galaxies, so that it was clear that these supermassive black holes lived in the middle of galaxies. Well, the long and short of it with this whole mess with high energy galaxies is that early on, these black holes are very active and they're emitting a lot of high energy radiation that doesn't fall into the event horizon and get trapped. It's being flung out at very high speeds, and we see that in objects like this quasar. But when they clear out enough material around them, they become quiescent, they go to sleep, they relax, the energy dies down, and we have a sleeping, normal, low energy black hole like the ones that we believe are in most all galaxies now, including the Milky Way. Not dwarf galaxies, which don't have enough mass, but most normal galaxies have a central black hole. So that was the big mystery of high energy galaxies. Well, a lot of great examples of these you can see around the sky in telescopes, backyard telescopes even. This is Perseus A, it was called, NGC 1275. That's the giant beast of a central galaxy, a CD galaxy. It's called centrally dominant galaxy. In the Perseus galaxy cluster, you can see, just looking at this image, you can see the chaos that's going on in this galaxy, which is powered by a very massive black hole that's very active in its center. And so what reawakens these black holes into chaos like this is when more material falls into the black hole. So it's quite likely when our galaxy merges with Andromeda, we will have a shaky, crazy, energetic future ahead for a little while. Galaxies exist in a gently balanced state, however, between grace and internal upheaval all the time. Sometimes they can go through these episodes of reawakening when stars or gas or other things fall into the centers, and they can have what's essentially an episode of the cosmic flu, if you will, that lasts for a while. We know our Milky Way and Andromeda will combine eventually in a favorite galaxy of ours in the southern sky, Centaurus A. This is maybe what Milkomeda will look like in the future. This is the result of a merger of two normal galaxies that have made this large elliptical mess, if you will. Many of you have heard of cosmic inflation, the period right after the Big Bang in which the cosmos hyperinflated almost instantly from about the size of a pea to about the size of a larger than a grapefruit. And we can't get into that right now, but if that happened, which most cosmologists believe it did, it explains a lot of what we see observationally in the cosmos today. But let's set that aside, because if inflation is true, it means that the universe that we see is not the whole universe. And in fact, the universe could be infinite. But let's be conservative and put that aside and say just the visible universe that we can see, it's a large place and it's spread out. The visible universe that we can see has at least 10,000 billion stars in it. And we're in a very, very exciting time now because we see planets around us in the Milky Way, everywhere we look around star systems, as we would expect. We know that chemistry is universal throughout the cosmos because of spectroscopy. And we know that, that the building blocks of life, the simplest amino acids, for example, are in the only samples of comets that have been returned to Earth. So the idea that life could be common in galaxies is not too big of a jump. But of course, right now we know of one place and one place only with life in the universe right here. We also know that the cosmic distance scale, even to the nearest star, is incredibly, unimaginably large. Galaxies, this is kind of a new phase of research, if you will, that's just getting under its feet. Galaxies may have zones where life is more likely or less likely, habitable zones, if you will, in galaxies. Rocky worlds, as we understand it, would offer the best hope, of course, of life, and that means metal-rich stars to make rocky worlds. A galaxy like the Milky Way may have a habitable zone mainly in the spiral arms and from about 10,000 to about 30,000 light years out from the center. That means we would be out a little bit far away from the preferred place for life. Farther out may mean fewer metals and less of a chance of rocky worlds. Farther in may mean greater dangers. But 98 years to the night after Hubble and his major discovery, we're still finding out incredible new things about galaxies and how they live. And just quickly, I will mention the book that came out a year ago that I wrote from Random House. It's called Galaxies. It has even more that I said tonight about this subject. And another recent book is Cosmic Clouds that I wrote with Brian May. And then all of this you can follow, of course, in Astronomy Magazine. So Scott, I don't know that I talked so much, I don't know that we have time for questions, but I will end the show and turn it back over to you.
Okay, all right, that's great. I'll read, let me go through this, but Harold Locke has a comment. He says, David, your presentation begs the question, excuse me, that intergalactic travel might be responsible for our UAPs. So,
well, we don't know, but intergalactic travel, we love movies and we love TV shows. And boy, I don't know what I'd do without them. But in reality, intergalactic travel is a tall order. because photons can travel at the speed of light, 186,000 miles an hour, as they're doing now off our computer screens and from light bulbs, because they have no mass. Consider the distance scale, which I didn't get into, but I'll try to make it quick, in our solar system even. Okay, we've traveled, if you consider one astronomical unit, the distance between the sun and Earth, as 1 centimeter, so that's about that big, we've physically traveled a tiny, tiny, almost invisibly small fraction of that. The edge of our solar system, just the Oort cloud, the inner edge of the Oort cloud on this scale is 10 football fields to the right on that scale. The nearest star to us, Proxima Centauri, is 4 times that distance. So to travel with mass, things like a spaceship, spacecraft, a crew, and go these kinds of incredible distances may be a very, very tall order, regardless of the technology, because of the laws of physics or the speed limit. So I think it's going to be a very tall order to physically travel around and have people land in Central Park and go to dinner on a tavern on the green with us and shake hands with us. But we may know of a lot of other life out in the galaxy and even elsewhere because of SETI. That would be my quick answer.
Yeah. So it is Go ahead.
Yeah, I do have a comment. I wanted to thank David
go ahead,
for
David.
his wonderful talk about galaxies. One of the comments that I wanted to make on it is that you don't need any money to look at galaxies. In fact, if it's later tonight or tomorrow night, you go outside and you look up out a telescope, out binoculars, you just go to a darker site and you look up and you'll see the Andromeda galaxy as it appeared over 2 million years ago. And while I have the floor here, I'd like to say that while I was listening to your talk, I got an email from William Shakespeare, and he said, why don't you get this right? The comet that I was writing about and that you quoted was the comet of 1599, which I was observing as I was writing Julius Caesar. And I wrote him back and I said, Will, I did say that, 1599. And he said, no, you didn't. I said, yes, I did. And we had a big argument. We're not talking to each other anymore. Anyway, David, good presentation. Thank you.
Thank you so much, David. And what a special thing it would be for people to go out and see the Andromeda galaxy 98 years to the night after Hubble's discovery. That would be pretty cool.
Yes, that's right. The implications of all of this, it just boggles my mind sometimes because, it's the research, the work, the effort that humans have made to try to understand where we live, how do we fit in, what does it all mean? Okay. It's been amazing. It's been amazing. It's an almost unbelievable story. And, so it's a hard look at ourselves, yourself, so these are things, these subjects that we bring up in Global Star Party are not things that are somehow apart from you. They are very much a part of you, right?
Absolutely. And of course, as we've talked before, we're literally our bodies are made of atoms that were created in stars. We're literally star stuff. And I don't think, if any friends or associates of us are ever lacking perspective, boy, does astronomy give us perspective.
Yes, it does. Yes, it does. Jason Gonzell, also known as the Vast Reaches, commented. He said, "Amazing, such a great presentation." That's very nice.
Thank you, Jason. Where do I send a check?
Chris Larson says, "Excellent presentation." He said, "This is why I rushed home from work." So, very nice, very nice. Beatrice is saying good morning from Belgium. So you have a worldwide audience, as you normally do, and it's just really been wonderful. David, thank you very much for this presentation. Who else could put together, encompass all of this and just, half hour, 45 minutes. So it's really amazing. Thank you. Thank you.
Thanks so much, Scott.
Thank you. Up next is Maxi Falares. Maxi is down in Argentina. He wanted to be part of this presentation. I'm glad he is. I know that he also rushed back from something that he was up to. So Maxi, are you all set up? Let's see. He's there. Let me ask him to unmute. Hello, Maxi. Oh, he says he has to wait some minutes. Okay, I got a message from him. Okay, I tell you what we'll do. We will just move on to the next speaker, which is fine. And let's see. Let me get my place in line here. Do we have Gary Palmer on with us right now? Gary Palmer? No? Okay. All right. Then let's move over to Molly Wakeling. I know
Hey,
she's here.
guys. Sorry.
Oh, you are here, Maxi. Okay. Sorry about that.
Yes, I was having some troubleshoots doing the live view from my camera, and well, I have. Do you hear me?
I do.
Okay. Well, let's wait a minute.
And there you
Okay.
are.
I'm here. I have a teacher from Ohio University, but that's a friend who well gave me. Well, thank you again for inviting me. Hi everyone, good night. And tonight what I'm going to show is a little tour from the southern skies. If you want to see something from here, in the city I have some issues with the light pollution, but some pretty cool global cluster you can see. I'm using my CW camera, putting on my equipment. So, well, I want to show my screen. Okay. Okay, do you see it?
Yes, we do. Wow.
Excellent.
Nice.
Well, this is the background of my notebook that is outside on my backyard, and right now I'm guiding to M7 Scorpius. Well, the guiding is very low. I think I have a little wind, but I want to show you some live view from the moment. And well, it's connected, and I want to do some pictures in 10 seconds of what of how is it. Well, I think this global cluster, this open cluster, you were able to see it from there. Well, this is a live view of M7. This is right now. What?
Wow.
10 seconds
Okay.
before.
Live view.
A live view, yes.
There's a lot of stars. A lot of stars. Look
A
at
lot
that.
of, and also the dark nebulation here at the left.
Yes.
And well, right now it's very low here. I'm using Carte du Ciel, and well, I think the side of the Scorpion you were able to see in the northern skies, but this place to here, I think is very complicated for you. And right now, here I have Corona Australis, this place, and I want to stop the guiding. So, okay, let's put it again, and we're going to be in NGC 6726. So I hope the the mount is okay. So let's go into C. Well, we are going in hyperspace point like Star Wars,
That's right.
that movie. And okay, so here we have a global cluster, and also this place is very spectacular. Oh, sorry. And well, this is 10 seconds before, and well, let's stop and put it a few seconds less, so we can start to move. Well, you can see this. There's nothing to see right now, but to the west, yes. Oh, it's too much. I think it's okay.
No, Maxie, I like seeing the live view through telescopes like this because, you can see the,
What is in there?
yeah, you can see what is in there. It's like having an electronic eye on the sky, and all the way, I can't hop on a plane right now and go to Argentina, unfortunately,
Oh,
but here we are.
it's
Here we are. We're in your
It's-
eyepiece.
this is my live view from down here.
Wow. Wow. Okay.
So this is a global cluster,
Yes.
and this is the two stars that shining and reflecting in the dark nebula,
Yes.
and also this place here, it has the same region. And I think in this place is a new solar system creating right now. So it's almost 500 light years from us. It's someone of the approaching solar systems in here. So let's do it a picture of maybe 1 minute. So let's keep talking. And
What a difference
also,
a minute can make, huh?
I'm guiding right now, so I think the guiding, well, it's like the hard test, and well, this is a double star, I think. This is unfocused. These are two stars, and
So close.
it's so close, but you can see. Oh, sorry, I don't think you can hear that. Well, that's the APT tools. Well, you can see at the background, it's a lot of stars, but here in this place, there's only a few. That's why in all this place we have nebulosity, and I think right now it's going to be more sharpened. This is like we have smoke,
Yes.
but they are very dark nebula that it's in front of the stars that they are behind of it.
Yeah, you
That's
can
why-
see, Maxi, that you can see that area has less stars.
Mhm.
Yeah, because you can see just the faint nebulosity. That would probably be like what you'd see visually.
Well,
I love this. This is beautiful.
Nico Arias, he told me that he saw with his Dobson this place in the farm doing only observation, and he told me that it's a good place to watch because you almost see this kind of reflections on the stars of the nebula, and also in this place here there's a light, well, tiny galaxy,
Yes.
but there's not very tiny right now. So
This is such a cool region. Is this the same one you showed before, Maxi, where you basically have every object within this field of view, right?
exactly. This is all
Yeah.
the field of view that I have with my F4 and comma corrector
Mhm.
for an F4. And well, also you got in this place everything. You have a galaxy, you have a global cluster, you have double stars, you have nebula, you have everything. This is a very good spot to watch and also to take pictures.
Yes.
And this is amazing. So, well, let's see if we can go another place from here to the south. In the south, well, we have the global cluster of the Peacock or Pavo is here, NGC 6752. So let's stop the guiding. This is more in the region more to the south.
You know, Maxi, we had a question earlier in the audience, and they wanted to know how someone who was disabled could participate in astronomy, you know. And, you know, of course, if you're physically disabled, if you can operate a computer, you can operate a telescope, just like what you're doing right now.
Exactly.
And in fact, share that with the entire world as we are right now. And, you know, it may require some setup that you get initial assistance with, but absolutely can be done. You can also access other remote telescopes like the Mark Slade Remote Observatory. There is the SLU service that's out there. Actually, there's a number of remote observatories that you can access, and you can be involved in professional/amateur projects to search for asteroids or to search for many different kinds of things that are in the sky with, you know, orbiting observatories or other types of observatories where they invite amateurs to participate. We have a young girl, an 8-year-old girl in Brazil, and Nicolina is her name, and she'll be on one of our programs here in the next week or so with JPL's Dr. Rosalie Lopez, and they will be talking about her potential discoveries she's got 18 asteroid candidates now being confirmed, and if she gets a confirmation on one of them, she'll become the youngest research astronomer in the world. She's working with the Catalina Sky Survey program.
You know, I saw from a national media from here, from Argentina, that they put that story of this little girl, you know, and also they posted a max photo that she has with a mount, and you know, whoa, this is incredible, and of course, this encourage to everyone to start stargazing, you know.
Yes, that's right.
And get involved in all of this because this is, I always say that this is only the a single only way, or how to say it, es un camino de ida, so it's you can go back, it's only forward.
Right.
So
that's right.
And of course you can do anything. You can do observations, you can do pictures, you can do studies. Today the technology that we have is amazing. With simple equipment you can do a lot, and then you can start to do some other things. And well, this is the Peacock global cluster here in the south. Right now I'm taking pictures in 1 minute because the color maybe will be very white, but let's see what we got. This is a place where is it right now, you know. Unfortunately, Alpha Centauri and Beta Centauri I'm not able to capture because they are very low, and I have my house and in my city. So I can do in all
But I
this
see two
place.
huge red chunks, which must be the large and small Magellanic Clouds.
Exactly. Yes,
Yeah.
of course. So right now I want to show this kind of quadrant of this place, and then maybe I don't know, now 1 hour more later, I want to show this other place that will be more up, you know, like I show in a couple of weeks ago with Adrian. I want to show you the Tarantula Nebula, the 47 Tucanae, the global cluster. We have Acharnar, and also a lot of galaxies.
Yes, please.
All right.
Well, I don't know what happened. What is very low here? No, it had to be more time. Why? What?
Yeah, I think Molly likes the southern hemisphere.
Did you came here sometimes,
Yes,
Molly?
I went to Chile in
Chile.
2019 for
For
the
the solar
solar
eclipse.
eclipse. Yeah, and went up to the Atacama Desert and did a lot of astrophotography.
Yeah.
And I'm planning on returning to the Atacama Desert at some point. So
Excellent. Excellent.
You know,
it was
Bart Bach,
awesome.
Bart Bach used to say all the good stuff is in the southern hemisphere. And that wasn't too much of an exaggeration.
Yeah, that's true.
There's so much good stuff down there. And what they're missing out from the northern hemisphere pales in comparison to what we're missing out.
Yeah, it's more weighted to the south, that's for sure. I
Yes.
agree, Molly.
So,
Yep.
so Mr. Eicher, do you know if Edwin Hubble went to the southern hemisphere to see the stars?
I don't believe he did. I'll have to check on that. If he did, it was South Africa, I presume. I don't think he did, though. Because the Boyden Station was down there, but I don't believe he did. But you've given me a research project, as they say now.
Yeah, it'd be interesting to know. It'd be interesting to know.
Well, here's a 30-second picture that changed something. And this stars is a very blue that contrasts with the golden stars.
Yeah, I was just on the webinar.
That blue star looks almost more like it's in the foreground than belonging to the globular cluster.
Yeah, hi, Jeremy.
In front of it.
Yeah, if it's blue, it's a foreground star.
Let's see, it's almost 9 seconds because now I'm guiding again. So it will be more without the star trail. And well, it
I
doesn't
love
change.
globular clusters. They're, first of all, cool to look at because, especially visually through a large telescope. And secondly, because of what they are, they're ancient. These things are 11 billion years old, which is crazy because some globular clusters are older than their host galaxies. And there's some thought that globular clusters were around before galaxies were. And
they all are, Molly. They're all older than the galactic disk.
Okay.
And there was a staff member at astronomy years ago who used to say, when we did stories on globular clusters, all globular clusters look the same. And I thought, oh,
what?
Shame on you. I thought.
Photographically, they kind of do.
You show me the guys that said that, and I'll smack them on the back of the head. Come
Photographically, they do kind of look quite similar, but visually, that's when you start to see shapes in them.
Yeah.
You can see, and I don't like to image globular clusters. And it's never really the same experience as seeing them visually. So I don't really image them much at all. But I love looking at them through big juicy Dobsonians.
It's when I see, for example, Omega Centauri or also 47 Tucana, it's like you are seeing a little shiny diamonds.
Yeah.
And they are concentrated in in that globe that looks like a cloud, and that is if you not watch it directly, you watch it with the left or the right of your eye, you can see how it's shining. That's amazing. And of course, if you are using a Dobsonian with a huge aperture, wow, that's a lot.
Yes, that technique we call averted vision.
Yeah.
You don't look right at it. You're kind of, you relax your eye, you relax, and you look away, and boom, something very faint can turn on. This is a great technique for galaxies, of course. But if you're looking at a globular cluster, wow, all of a sudden, what looks kind of like this tight ball now is growing, okay? Because you're starting to see, thousands and thousands and thousands of more stars, the faint ones.
And also, you start to feeling the photons that they arrived and
right.
travel. That's a lot of light years, and you start to realize how is it all that.
Yeah. The other thing that's interesting to think about is if you were on a planet around one of the stars in one of these globular clusters, you would have hundreds or thousands of stars the brightness of Sirius in your sky. You probably wouldn't be able to see outside the globular cluster, really. You might not know those other galaxies out there. If your star had, if you had so many stars that were as bright as Sirius or Jupiter, you'd probably have a hard time doing astronomy.
Well, a couple of days ago, I simulated a vision that with a sky portal you can do is a travel to the orbit of that star, and whoa, that's changed a lot, and also changed a lot of perspective on other stars of where they are and how we see from here. And some stars they might be in the same place, but another ones they say, oh, but this is Antares. No, it wasn't there, for example.
Yeah.
But that's amazing. Well,
you
yes,
turned your camera cooler off. Did you mean to do that?
I it's with the power supply connected, but
okay.
I well, let's get cold. You are the expert, Molly. I am the newbie here. I only have 1 month with this camera, and well,
it makes a huge difference having the cooler on. I was on I think I was on here several months ago or earlier this year, and I forgot to turn my cooler on and took 2 back-to-back images of the Crab Nebula with the cooler on and the cooler off. And with the cooler off, you could barely see the Crab Nebula, but with the cooler, because the noise was so high, but with the cooler on, then it really popped right out because the noise
it
was
contrasted,
so much lower.
Right?
Yeah, the contrast was much better because the noise was a lot lower.
Oh, excellent.
It makes a bigger difference than you might think.
This camera has I think you can go maybe 20 degrees under the zero, but it doesn't have glow. It doesn't exist.
Yeah,
you're doing maybe 10 minutes pictures, and the glow, it doesn't appear.
That's nice.
Well, you're seeing the Peacock Galaxy. This is very near from that globus cluster, and well, also in the Peacock. I don't know whether they saw a peacock here.
And you're just these are single shots, right? Yeah. This is not. You're not doing any live stacking. This is just a single.
No, a single picture, and because I'm guiding right now, and also taking pictures from 1 minute. Well, the gain says low. I don't know how low it is, but I think maybe 100. I don't know. But
How
the
how
the
dark? Sorry.
the histogram in this program, this is the ASI program from the manufacturer, and puts auto. If I reset it, you doesn't see anything.
Yeah.
So let's put it out automatic and shows everything.
How dark
So
are your skies?
here in my city are both 6 and 7, and right now I'm pointing, of course, to the south, that I have the center of my city. So I have LED lights, LED lights, and all this place is like a glow white.
You're
When I
getting
go,
a really nice picture despite that.
really, well,
Yeah.
it's a small town. Maybe well, I did. I post a picture of the quartet of. Oh, I forgot the name. Sorry. I have the picture here. Do you see the picture, the screen, or you are seeing?
We are still seeing any desk.
Ah, sorry. I have to stop sharing and let's go again. So this is the picture that I took a couple days ago. And for example, let's see someone. This is only a single picture.
Oh, that looks great.
And these are.
That's nice.
Oh, I love these.
Nice.
I love these.
Yeah.
That's nice.
This is the quartet of. The name goes out from my mind. Sorry.
Yeah, the Leo trio, right?
No, not
Or
this
is it?
one.
No. What is this?
No, this is a different one. Yeah.
It's
not the box. It's not the box either. This is a different one. This is a southern hemisphere one.
Yeah.
Sorry. Let's go. Sorry, it's a shame of me that I don't remember the name. Sorry.
What constellation is it in?
I don't remember.
You don't remember?
Yeah,
Okay,
that's
no worries. No worries.
My mind is right now blocked.
It's okay.
It's one of the billions of galaxies out there. Yeah.
That's a
Or one
tip.
group
That's a tip to put the name in the file name.
Yeah.
Yeah, I'm like I said, I am a newbie.
Yeah, but you're taking pictures like a pro, so very cool.
Yeah.
It's cool. It's really fun when you're starting, you have the new gear and you start taking pictures. You found it?
The quartet of Grus or
Oh,
Grusha.
yeah, that's what I was trying to, because I've seen this visually. I saw it visually when I was in Chile, and I was trying to remember what constellation it was. But yeah, Grus.
Well, here are only 4 principal galaxies, but there is a lot, really a lot of galaxies.
I really love when you can see the different types of galaxies. I mean, kind of going back to what David Eicher's talk, the Hubble classification of galaxies and seeing different types. I love like barred or edge on or elliptical, different angles of different structural, all in the same view. Like these are just beautiful. I love this pairing. It's really nice. And especially, I mean, that's with photographically, but to be able to do it visually as well with a larger dot is really nice.
I couldn't believe it when I took this. All these kind of galaxies.
Yeah.
And in this place, and I don't know if in this place there are a gravitational lens.
Lensed. Yeah.
Exactly.
Yeah.
That maybe because it looked like a world.
Right. It looks like an Einstein ring around it.
It kind of does. Like you can see the kind of the 4 dots along the edge there. It's high on my list to do one of those gravitationally lensed galaxies next time I go somewhere dark.
Well, another thing that's a basic thing. I mean, think about it. This is basic equipment. And you're actually seeing redshift. I mean, you can tell those galaxies are further away by their color. And so depending on the colors that come through, like as you start to see further and more orangey or yellow, I mean, maybe Molly, you can talk to this more, but you can start to see just by the colors, you're actually seeing the distance in a way, right?
Yeah, I'm
I
trying
don't
to
know.
possibly. I'm trying to think at what point you kind of it starts to become more noticeable. I know you can like the little guys in the back of images. I've gotten ones showing up in my images that are as far as 300 to 600 million light years away. I don't remember offhand where the redshift starts to become obvious, but you can also, there are some quasars that are magnitude 12 or 13, easily within the reach of stacking images from an 8-inch telescope. And doing one of those has been on my list as well. There's no detail in them, they're just kind of blobs, but you know that you're imaging something that is 1 billion light years away.
100 million, like I don't know. I random a galaxy in Sky Portal, and when I go to the info, they say it was 800 million.
Yeah.
Light year, what?
Yeah, some of those little guys in the background are several 100 million light years away, which is extremely cool. And just
blow your mind.
Yeah, it blows your mind.
Yeah, 100 times further than what
that
Hubble
is the
thought.
most accurate statement tonight. Yes.
Yeah, exactly. A whole order of magnitude further. That's
and look,
amazing.
there's a little cluster there. Check that out.
Of galaxies.
Yeah,
now,
little
Maxie,
galactic cluster.
What size telescope are you imaging with?
8 inches, 200 millimeters.
It's a good size.
You are seeing an imaging stuff that is so far away with only 8 inches of aperture.
That's what gets me with astrophotography. Like,
beautiful.
The fact that I can throw this stuff, and we can throw this stuff in the back of our cars,
right?
Drive, take it somewhere, set it up in an hour or so, or maybe less, and image things that are hundreds of millions of light years away. I mean, think about what people would say if you were telling to them like 100 years ago or 50 years ago.
If you were hanging around Giordano Bruno, you would have been burned at the stake for it. So
yeah,
like he was.
Well, even the technology we have for a few $100s used to cost millions of dollars 20, 30 years ago.
Yeah.
Right.
That we have in our, we have in our hands.
That's right. Wonderful.
Well,
thank you.
That's for now. I hope, or if you want to be tuned, maybe I don't know if 2 hours, but
come back.
I will be online, but maybe to the after party if you will be tuned.
Sure, of course.
Maybe we can be in 47 to Ghana, or also the Tarantula Nebula, and other galaxies like the Sculptor Galaxy, but there are some another ones that I will have. Really, I hope the clouds does have a problem. Let's see the weather.
Well, there's a lot of things that we can see from the northern hemisphere, but they're very low, like a lot of things in Sagittarius and Scorpius. So having them be up high for you gives a much sharper and nicer view than we can typically get from up here. So you might have a better view of the Sculptor Galaxy than we get because it's so low.
Yes, I will have it over my head. And also Sculptor Galaxy, if you are in darkness skies, you can also watch it with binoculars.
Oh, nice.
That's amazing. Well, thank you again. Thank you for inviting me. And well, I will be here. I will be listening. I have to do some other things, but I will be in the after party to still showing some part of the southern hemisphere.
Wonderful. Well, thank you for taking on this wonderful voyage. So we're going to go from Argentina now to the UK, to Gary Palmer. Gary, thanks for coming on.
Hey, Scott. Hi, everyone. Hope you're all well.
Yep. Everybody's good. I think so. It's been a fantastic voyage learning about the expansion of the universe, and and it's not over. We've got some great programming coming up, so including you, Gary. So let's
Yeah, it was quite interesting this, because you said to me about it and I went,
Yeah.
as usual, yeah, no problem, we'll jump on that and get on it. And I thought, we've imaged some stuff this week, let's have a look and try and find it. Easier said than done.
Right, so I challenged Gary to
Yeah.
find
So,
the Cepheid variable that
it
Hubble
wasn't-
found in 1923.
Yeah, it was a little bit of a headache, and there are a couple of reasons, and I suppose we take a lot of this for granted now, because I looked at the plates. That was the first place I went, just have a quick browse over those.
Mm-hmm.
And the first thing that's noticeable is you're lucky if you've got 30 stars in an image on the plate. Yeah, maybe a couple more. Whereas I'm looking at one of my images from this week, and there's somewhere around 2,000 stars. That's
Yeah.
close in the image. And also the way that our cameras are really sensitive, filters we use, everything else. So now we can bring out all of the dust lanes, and you'll notice that on the plate side of things that the dust lanes are not that visible. So it's only really the core, one of the upper dust lanes that's visible. So it was quite a challenge to try and drop in on the area and have a look and see what was going on. But I have been listening into some of the program, even though I've been quite busy on some other stuff, and listening to David, and that was quite interesting on a lot of the explanation to the galaxies. But I suppose in our world, they've got very, very popular now because they are easy to image. That is the key thing. And you can go out and image galaxies with very, very little equipment now, really a camera and a lens, and you're starting to pick up some good detail. And certainly on larger galaxies. So I thought we'd have a look at this and see how we managed to sort of home in the area. I did pull up the Hubble image as well, to sort of try and reference this off and work from there. And I have to say, it took most of the afternoon to really drop in anywhere close to this on the images. So if I share the screen over.
Now,
Wondered
before
if
you
it was
show
possible.
it, Gary, before you show it, how long was your exposure?
This is an hour. Now, we were clear earlier this evening, so I did try.
Okay, an hour exposure.
To grab a 3-minute shot of this and see whether we could do the same thing, hoping that it would actually cut down on the stars in the image. Generally, when we image Andromeda, quite a lot of people will remove the brightness, the intensity of the stars, just because there's so many now with the modern cameras. So this is what makes it quite hard. And if you're looking for something quite faint, the last thing you want to do is just start removing the intensity. So if I share over this screen.
Did you try doing any kind of plate solving on the original Hubble image to narrow down the location?
The issue is, if you actually start going into this, it's not that well documented on exactly where it is, apart from Hubble images and the original plate images. If you start running into Sinbad and different other areas and trying to locate it, it's really, really hard.
Right.
And I know that there are some papers written on it, but I didn't have enough time. There is a HD number associated around it. So it's really, really hard to actually reference it. So the image that I was working on, if I just transfer this over, give me a second.
Now, Hubble's image was a 45-minute exposure.
Yeah.
Okay. In 1923, and you're only getting a tiny fraction of the view, just because of exposure that you are here in the shot that you did.
There we go. There. That was the Hubble image taken. So that's where the area that we're looking in, and we're certainly not going to get into this resolution here. But even this is blown up around 600 times.
This is Hubble Space Telescope, right?
So again, I didn't hear.
This is Hubble Space Telescope.
Yep,
Correct?
that's it.
Yeah.
So it was sort of referencing it off of this, having a look around and trying to work out what was going on. So first thing was start getting it all together, get it into PixInsight. And then I thought, there's way too many stars in there to start really having a look around for something that small. So maybe to actually invert the image. So I took different things, took the stars out, did other things to try and come up with this image here. But what I was actually doing was working on the mono. And as you see there, I'd inverted it in the background to try and bring it back to sort of the plate. So you're trying to remove as much of the stuff in the background to jump onto this. And it is really, really awkward. The color cameras are not easy because they're actually adding more noise and more distortion to the image. So that's the key thing. And I don't have any current stuff from mono. So going on their image, I came into this area here. If we zoom out on this, actually see that it comes into here. What it doesn't do is really show up that well compared to the Hubble image in mono. So then you have to go back to the color once you found the area, and bring it up in Photoshop and start playing around with it in there. So I'd actually ended up, if I zoom in on this.
You know, Gary, I assumed this would be a slam dunk. I thought that you would be able to get this Cepheid variable so easily.
I mean, we did have quite a bit of high cloud in the week when I was running this, so that's causing some on the edges of the stars. But we're in this area here.
Okay.
Exactly in there. From what I can make out, it's either this one here or this one here.
I see.
It's so hard to tell from the Hubble image. I haven't got a blown up copy of the plate. I'd need to download it and play around with it and rotate it in the right directions to pull the stars out. But that is the area that it's in. And that's referencing off of these Hydra and Alpha areas here. And the blue stars here. And if you actually follow this circle round on the Hubble image, you end up with this little dark structure there. Now it's showing two stars. Now I've got a green star there that's actually showing as green underneath it, but these are really, really faint. These are really hard to see. And when you look at the Hubble image,
not even sure about the star or a noise pixel.
So when you're looking at the zoomed in Hubble image there, that's how tiny the star is. So really a little bit of this was, well, the equipment out there was a 90mm telescope. Can we resolve it with that? So I think we're not far off of it. And probably if we had a mono camera on there, we would resolve it. But,
and one thing to absolutely say is that although, that shot by Gendler and your image is amazing in the amount of detail that's there, when you look at the resolving power of the stars, how tiny the stars are and how far they're spaced apart with the 100-inch, even seeing it from 1923, you can tell the advantage of aperture,
Yeah, you can, and that's the key thing. And, I'm fortunate enough here to have a dark sky site. If we had a sort of another week or two on this, I'd probably put one of the 925 up or a 10-inch up and drop into the area with a close-up mono camera. And we would probably resolve it quite simple. But I did also go back on a couple of images, but most of the images I do of this sort of thing, the galaxies, are normally one-shot color. So I haven't got a lot of mono detail on this, but I have to say it's not the easiest of challenges that I've wandered across, but then
it's kind of like trying to recreate the Wright brothers aircraft or something, so they flew in Kitty Hawk, but there have been lots of students and scientists that have tried to rebuild a flying model of the Wright brothers aircraft, and it ain't so easy.
Yeah, that's the thing. But if you look at the plate, you can see that the stars are quite defined. And even if you're looking at the color image here, there's far more stars in the area. So the color is going to distort on some of the stars. but switching it to mono just makes it really, really hard to try and locate it exactly. But I was actually surprised that there's not a lot of reference into it. There's a lot of reference into, you know, the advances in astronomy that were made through the star, but not actually referencing it on its location and different other things.
You would think that there'd be other astronomers that would want to repeat these measurements to verify that it is the Cepheid, and that's a true case. There would be records of that, it seems like.
Yeah, I mean, I did do some quite extensive searches on it yesterday. And as I said, there's a couple of papers on it, but there's not a massive amount sitting around on it. It's in, I think the issue is that once everybody gets up to Andromeda, they want an Andromeda image. And to pick off a star, it just doesn't happen.
Right.
You know? So a lot of other people might be looking at it, well, they're going to walk into the same area that I have, that it's going to take a lot of power to resolve it. So you're going to be 10, 12-inch telescope, something like that, to get in there, and in a fairly dark sky site to do it. But I did have I think it was that one. Yeah, this was one of the images from earlier today. So we're in the same area there. Yeah, so we're circling around on those into that area there. And I'm pretty sure it's that one there that's showing up as green. Yeah, in the actual color, one-shot color image.
I think it's.
So there you go. That was as far as I got with your challenge, in a sense.
All right.
We were there. You know, it is there, and I think if I played around with it a lot more and drew it out, that we would get it. But from the data that I've got on file, certainly from this year, if I have a look back through last year's stuff, we might have some stuff there that might be able to pick it out. About 8 years ago, I did some close-up stuff on the dust lanes, so there might be some files there that would hold it.
Yeah.
They were done on sort of 10-inch, 12-inch telescopes at the time. Lately, in the last few years, really, it's just about grabbing the whole of the galaxy and getting as much detail as possible. So,
right.
Yeah, but very interesting anyway. It was interesting reading up on it, and certainly interesting looking at the quotes and some of the other things.
I'm glad you dug into it. You know, sometimes I like to go back and see what you can find in old images, and you know, just to try to put all the pieces, the connections together. You know, because it all connects to right now. You know, so it's part. You know, it is part of this continuous journey of exploration and discovery. And it's great to be able to look back on these historic images. You know, so.
I can see why a lot more things were discovered in the past than what are discovered now. I think there is a lot more there. You know, we know a lot more, we see a lot more, and we have a general thing of sort of going through, you know, a list of targets, or we see an image online somewhere and we think, yep, I want to image that, and away we go, and we're off doing that. But I always say the same thing, that once you've got a camera on a telescope, you lose 99.9% of the sky, because that telescope's trained on that object for X amount of hours. You know, it might be, you know, 50 hours through, you know, a month of capturing that target, and all that time, other things are going on. You know,
comets are coming, all kinds of stuff. Supernovas are exploding. You know, so
and it's very easy. I think social media has helped with it, because you see a lot more images coming online. You know, and when you look at some of the arguments that were going on at the time around this, you know, and believing that Andromeda was part of the Milky Way, you can see where it was going, and the way that people thought on that, just by their limitations. You know, the limitations in the equipment.
Sure.
But yeah, very interesting.
Very cool. Well, you know, John Briggs is waiting in the wings and comes on in a couple of speakers. But I like this idea of challenging astrophotographers to go back after some historic discoveries. So you're likely to see another a challenge come from us. So I'll collaborate with John on that. You know, 'cause I know that
It was a shame
would
tonight.
be a good source. You know, to
was a
say, well,
shame.
Scott, did you think about this one? You know, so
Pick me.
that's very
I want
cool.
to play. I want to play.
You want to play? Okay. All right. Yeah, any of you guys watching out there
I'm
that do
playing now.
astrophotography, you want to play with us? Then yeah, we'll have the historic discovery challenge. You know, so
Yes.
Yeah, we just need a few clear nights. We have suffered with a lot of high clouds, so I think that's what's, the last month has been really, really difficult on imaging here.
sure, yeah.
So, yeah, but it's certainly worth a revisit, I think, with one of the large scopes and just see what we can pull out.
Okay,
Just for fun of it.
very cool.
Gary, you've inspired me. I'm looking at some of my stuff, and I might have something to show later.
Cool.
Yeah.
Excellent. That's what it's all about.
Wonderful. Well, up next is Molly Wakeling. Molly's been chiming in on this program. I can tell her excitement was building and building as she was looking at Maxie's live views of the Southern Hemisphere. And, Molly loves a challenge. She loves science. And, we're so lucky to have her on our programs. And so, Molly, I'm going to turn it over to you for, I guess, another great episode of Astronomolly.
Yeah, Astronomolly's universe. I think.
Yes.
So I
Yes, it
kind
is.
of have an interesting topic tonight. Let me share my screen. Yeah, that one. Okay, let's hop on over to my presentation. All right, does that show up okay? Because I've got like an ultra wide screen now.
Yeah. Yes, it does.
Okay, cool. Are you seeing the presenter view?
Yeah, that's a
I
presenter.
think
view,
so.
Molly.
Okay.
Yeah.
Okay, yeah. Let me fix that real quick.
You go to.
I think there's actually a button that lets you swap. I thought there was. That's okay. I will do this. Share that screen instead. Okay, there we go. That should work well enough. Oh, weird. It's like captioning me now. Turn that off. Okay, sorry. So normally during this segment, I talk about an interesting deep sky object that I've imaged and want to dive deeper into what that object is and why you should care about it when you go to observe it. And I would have done M31 for tonight, since that would be the obvious choice. However, I just did that one recently, so I decided I needed another strategy, and I was trying to think of a target that was significant in kind of building up the distance slider that I had actually imaged before. And then I thought, well, have I imaged any Cepheid variables at all? So, because I do variable star imaging for the American Association of Variable Star Observers, and I have quite a bit of a backlog of data I'm still trying to work through from earlier this year. And so I went and looked at the Cepheid variable database and compared with ones that I'd imaged, and none of them were showing up. But then I thought, okay, well, I'll go choose another star that's just kind of interesting to talk about among variable stars and compare it to Cepheid variables. But then as I was annotating my data sets, I saw that RU camelopard. I practiced this earlier.
Camelopardalus.
Camelopardalus. I practiced this earlier.
I like it's RU camelopardalus. No, I'm not. No, I'm not.
No problem was I practiced it in my head, but not out loud. So I need to tell it to my cats.
Yeah.
And that it is actually a Cepheid variable, but a type 2 Cepheid. So that's why it wasn't showing up in the database as I was looking in. So I'm going to talk about this cool star. Are you camelopardalus?
Yes.
Which is a northern constellation that we are stuck with. Or are you Cam for short?
Yes.
All right, so what is it? It is a type 2 Cepheid variable star of a specific subclass called W Virginis. A lot of variable stars are named, the subclasses of variable stars are named for like the first star or a prominent star that exhibits the same behavior as the star. So like if you've ever heard of Mira variables or Cepheid variables are named for a star in Cepheus that was discovered with these characteristics, or RR Lyrae variables. They're named for like a prominent star that exhibits the same characteristics. So this is a W Virginis variable. And what's interesting about it, in addition to the fact that it's a type 2 Cepheid, is that it's also a carbon star. And it's pretty unusual to have a carbon star that is also a Cepheid variable. So I'm going to talk about what both of these things are in a minute, but that's kind of the first glance at what's interesting about this particular star. So where can you find RUCAM? It is in the Northern Hemisphere. So sorry, Moxie. And Cesar's on tonight. Sorry, Cesar. It's quite far north, as you can see on this finder chart here. It is in the vicinity, it's not too far away from M81 and M82, which my mouse up here annotated here. And we've got Ursa Major constellation with kind of the familiar Big Dipper. So it's in that northern vicinity. So some fast facts about it. It has a variable period of 22 days. So that's the time it takes to go from, actually, I can't remember if it's bright to bright, or if it's just bright to dark, if that's the full period or the half period. I meant to go look that up and forgot. It is 5,170 light years away. It was, I couldn't find, I mean, so a lot of these like kind of less, like things that aren't deep sky objects don't really have like it was discovered by kind of names, because there's so many stars out there. Like, you know, when has somebody discovered a star per se? But it was reported to be a variable star by Witold Swarovski in 1907. Has an apparent magnitude in the range of 8.1 to 9.8, which actually makes it pretty accessible to visual observing. That's not a very dim star at all. So easily accessible with cameras, pretty accessible visual observing as well. And it has a mass of a little more than half of the sun's mass. That symbol there is the symbol we use for solar mass. So what is a type 2 Cepheid? So the picture that's here in the background is one of my pictures with my Newtonian that I used to do my variable star imaging, and I've got RUCAM circled there in the middle, and it's annotated with its RA, the RA and DEC lines around it. So a type 2 Cepheid is they're generally population 2 stars, so there's 3 populations of stars. Pop 1 are, and it goes backwards. Population 1 stars are stars like our sun, stars that have a lot of metal content. And in astronomer speak, metal is anything heavier than helium. So like things that you wouldn't normally consider to be metals, like oxygen and nitrogen, are considered metals in the astronomy community. So it's kind of funny. Population 2 stars are older, don't have as much metals in them, called them metal poor, tend to be lower mass. And population 3 stars are the first stars, even though it's kind of backwards, that have almost no metal in them, because these were the first stars. They were just hydrogen fusing into helium. And we've not actually found any pop 3 stars. They tended to have shorter lives, because once they burned through the helium, there wasn't much else left to burn at that time. But as stars burned heavier and heavier materials, burning up the mass chain, then when new stars would form, they would be seeded with those heavier materials like carbon that it could burn later on in its life in order to live a longer life. So that's like our star has a lot of metals in it. Population 2 stars like type 2 Cepheids are a little more metal poor. And that influences their end of life behavior pretty significantly. Fainter than classical Cepheids, that I misspelled there. So classical Cepheid is like like the one that was discovered at M31. And but because these are population 2 stars and they tend to be more in the red giant phase, they're not as bright as classical Cepheids. However, like all Cepheid variables, they exhibit a strong relationship between their luminosity and their period. So type 2 Cepheids can also be used to calibrate the distance scale. Thank you for turning off your mic. It can also be used to calibrate the distance scale when there's not other available distance scale markers to use, because they have that relationship between luminosity and their period, which, just like an M31, allows us to know how what the stars like actual luminosity is compared to how we see it. And of course, it will appear dimmer if it's farther away. The W Virginis subclass are type 2 Cepheids that have periods between 10 and 20 days, approximately. There's not really hard cutoffs, and they're pretty fast and loose with the cutoff definitions. So 22 days, no, that's close to 20. It's going to be a W Virginis star subclass. W Virginis stars are usually at the point where they're having this periodicity, this variability, are undergoing hydrogen or helium shell burning as they're getting into their asymptotic giant branch phase, which I know is a lot of like stellar evolution words I'm tossing around here. But over here on the right, I have an HR diagram, or Hertzsprung-Russell diagram, that was a little bit poorly made, but one I found on the internet, that has the star's spectral class, which has to do with its luminosity and its surface temperature, and the absolute magnitude of the star on the y-axis here. And it kind of outlines the different types of stars. So here's the main sequence band where our sun lies, kind of more in this middle region here. And let's see, I spotted it earlier. Yeah, W Virginis stars are in this asymptotic giant phase, where it's changing between being kind of a more main sequence type star and becoming more of a red giant. So it's becoming redder and it's becoming brighter as they kind of progress through this branch here. And actually, the physical properties of type 2 Cepheids are not really well understood. So there's not a whole lot out there about what physical processes are causing them to vary in that way, and why they operate differently than classical Cepheids. So more work to be done there, it sounds like. Yeah, so it's also a carbon star, which is interesting. So carbon stars are asymptotic giant branch stars, basically luminous red giants, as we saw on the last slide. Their atmosphere contains more carbon than oxygen, and it's kind of referred to as being sooty, which is the opposite of most stars. Most stars have more oxygen than carbon in their outer layers. And this is a result of, so when a star burns out its hydrogen supply, it starts to burn helium instead. But helium doesn't give as much energy as hydrogen, so the star will end up compressing because it's not putting out as much energy to resist the pull of gravity. But once it compresses to a certain amount, the temperature rises, and that allows helium to start burning, which, and when I say burning, I really mean fusing. But kind of use burning and
yeah.
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 there's some analogies there.
Yes.
And it starts to fuse helium instead, which doesn't give us much of an energy return and requires a higher temperature to fuse. And you can kind of move up mass chain this way, and some other processes happen as well that eventually get you to carbon. And that carbon from deeper within that required the higher temperatures to fuse is then brought up via convection to the surface of the star. And then the light that's being emitted from the middle of the star has to pass through that carbon layer, making the star appear a very deep red. Long story short, carbon stars are red. Yes. And they have a whole lot of carbon in their upper layers. Now, this plot's not really related to carbon stars, but I didn't have another place for it. As I was looking for some details on RUCAM, I found a paper published in 1941 by none other than the famous Cecilia Payne. So that was cool to find sort of an original paper on her variable star work that she got into after her initial kind of major discovery that the sun was made of hydrogen and helium in her doctoral thesis in 1925, which was disputed at the time. And then later everybody realized, oh, she's right. And one of my favorite things about her paper, because I read through it, and she pretty much only references other female astronomers in this paper, which I just loved.
Yes.
It was really fun. So
it's cool to be able to dig through this stuff. So much of it's online.
Yeah.
And you can reach right back into history,
Yeah, and clearly these are hand-drawn plots, which we don't do today. But you think about the amount of precision that this is a scientific paper. You got to get those points exactly where they belong on these axes, and like that takes some work. And these axes are actually kind of hard to interpret. I was trying to read the caption. The figure caption is kind of odd, but yeah, this is data all for RUCAM. It's orbital period and visual and photographic magnitudes, which differ because of the photographic plates are more sensitive to red, while our eyes are more sensitive to blue, and lots of other information about it. So that was kind of a fun find. So observing, you can observe, are you camelopardilus? Camelopardilus. I keep putting the emphasis on the wrong syllable.
Yes.
So yeah, sorry.
No, move right ahead, Molly. Thanks.
Okay. So I mentioned earlier, it's pretty bright, relatively speaking. So you can certainly catch it in a telescope if you've got a good finder chart on you. And it is circumpolar for I didn't look and see what the minimum latitude was for it being circumpolar, but certainly all of Canada and the upper United States, and probably the entire United States and some of Mexico. It's circumpolar, but it's the highest in the sky in the evenings in March. Magnitude 8 to 10 is pretty easy to see in most telescopes under most conditions. And the American Association of Variable Star Observers does actually accept visual observations of variable stars. So there's a technique to it. You have to compare the brightness to some comparison stars visually of known magnitude, but they do welcome generally visual observations of a lot of variable stars. However, RUCAM is not really being actively studied. It's a legacy star, but I still submit data on it because it was a star that I could reach at that time of year. So I'm still processing that data from last March. Photographically, very short exposures. In fact, I was taking 30-second exposures on this rig here. This picture doesn't have the right camera on it. I have a QSI 583 on there now. And I was taking 30-second exposures and was overexposing RUCAM in most of the bands I was observing. So I've docked to 15-second exposures at 1x1 binning. And yeah, it's pretty easy to pick up. And you can submit photographic observations. I have photometric filters, but they will also accept transformed, what they call TG filter, which is, let's say you have a color camera or like a green filter, a green regular imaging filter. You can calculate some transformation coefficients with a piece of software they have, and you can submit observations even just without photometric filters. So it's pretty cool. So I was furiously this afternoon trying to go through my backlog of data that I have from March to try and put up a cool plot of all of my observations of it. But alas, I did not get very far. And I only got a couple of observations of it done. So here's a very uninformative chart, but it's a cool reminder that when I submit data to the AAVSO, it's in a database. And researchers and students and teachers can download data from the database to do analysis on. So my couple of data points here are part of a larger pool of data points. If somebody ever wanted to use this as an example of a type 2 Cepheid and plot its light curve, you could go on and download this data and do that. So it's very cool to be a part of science, and a lot of professional astronomers will pull data from their database to supplement their observations or to do some analysis on to support their other work. So I have submitted, I should have gone and looked. I'm in the several hundreds of observations submitted now of across all the stars that I do. And every week I get an email from the AAVSO saying which of my data sets were pulled as part of research. So it's very cool to be able to participate in that way as well. So yeah, that's Are You Cam and variable star, much like the one in M31 that really opened up our eyes to how big the universe actually is.
Yes. Yes, and the journey continues.
Yeah.
Well, okay, so we have come up, I think, to our first 10-minute break, which we're going to take, and then we come back to Jerry Hubble. Jerry, I challenge, like Gary Palmer, I challenged Jerry to research how Edwin Hubble actually measured the Cepheid variable in you know, in that old plate in 1923 versus how we do it today. So you know,
I found a couple of good, interesting things to think about, and we'll talk about that.
Okay, great. All right, we'll be back in 10 minutes. Stretch your legs, get a coffee, get a sandwich, and we'll be right back.
The Space Telescope was named for Edwin Hubble, the great astronomer who did much of his pioneering work in the 1920s at Mount Wilson Observatory in California. In those days, our own galaxy, the Milky Way, was considered the entirety of the universe. Nearly everyone, even Einstein, believed the universe had existed forever in its present state, that it was eternal and unchanging. But Hubble would prove them all wrong. He began by figuring out how far away the stars he was seeing actually were.
At the time of Edwin Hubble, it was hard to measure distances. It still is, even today.
It's difficult to know if a star appears bright because it is actually bright, or simply because it is close to us. So Hubble searched for a rare type of star called a Cepheid variable. Cepheids pulse at a known brightness, so by measuring the amount of light he could see, he could calculate how far away the star actually was. In October 1923, Hubble found a Cepheid in a gaseous cluster of stars then called the Andromeda Nebula. It yielded a shocking discovery.
When he actually did the calculations, he discovered Andromeda was roughly 1 million light years away from us, which was outside our galaxy.
Andromeda was its own galaxy.
Oh, there are other galaxies out there, and we're just one of them.
For the first time in history, there was evidence that our universe stretched far beyond the Milky Way.
But then what he did was, we measured the speed of a whole bunch of these galaxies.
Edwin Hubble measured speed by looking at the light the galaxies emitted. He knew if the galaxy was moving toward him, the waves would shorten and shift to the blue part of the spectrum. If it was moving away, the waves would lengthen and shift to the red.
Every distant galaxy Hubble looked at, he saw the light from it being redshifted, which meant everything is moving away from everything else.
And he found the further away they were, the faster they were going.
In fact, the universe itself was expanding, stretching the light from the galaxies. Edwin Hubble had changed our understanding of the cosmos forever.
The whole universe was clearly expanding. And so this was the discovery of the expansion of the universe, which Einstein said, well, that's crazy, right?
The discovery of the expansion of the universe, of course, was a very strong piece of evidence for a beginning. If everything is now expanding, you can run this backwards and see that everything should have started from a certain point or singularity, what we today call a Big Bang.
Hi friends, Vivian White here from the NASA Night Sky Network, and I just want to invite you all to join us for the Global Moon Party happening October 9th from 3 p.m. on, that's Pacific time, 6 p.m. Eastern time. We are going to have such a blast. We have great folks from the International Observe the Moon Night joining us. We have NASA friends from the Visualization Studio and moon treks and all over the place. We have Icelandic poets to talk about the moon, presenting new work that they're doing. Space agencies from around the world will join us, and we hope you will too. Please get the word out. Let everyone you know who loves the moon know that we are kicking off the International Observe the Moon Night this October 9th. See you there.
Okay, we're back.
You're echoing, Scott.
For some reason, I'm echoing.
Is it?
I was supposed to say it like this. For some reason, I'm echoing.
Isn't October 9th a new moon?
That's a new moon today.
Okay. Because I was thinking, like, it's going to be hard to observe the moon when it's when it's dark.
Well, it's the kickoff party, you know, so the kickoff party. So
The 12th
actually, I
is the
think
first quarter.
yeah, that week starts what, on the 12th or
Yeah,
something?
12th is the first quarter. Yeah. Today is the new moon.
Okay,
Yeah.
okay.
That's
And
right.
it's cloudy here.
Oh,
Yep. It's cloudy here too.
clear right outside those clouds, you know, so.
If only. I'd seen a build a really tall tower or a space telescope.
Molly, I really enjoyed your presentation. It was great. In fact, I've enjoyed all the presentations. It's awesome. And so I think from time to time, I am really going to seriously get started with trying to do the implications of historic observations, and then challenge our astronomers to make similar observations. I think that would be very cool. But up next is Jerry Hubble. Jerry he is one of the guys that is in the best tradition of amateur astronomers, where they break the boundaries. They do things that that a lot of people would think would be impossible for an amateur to do. And so Jerry's very involved with exoplanets, and he does this with a fairly small telescope. So but this week, we are focused on Cepheid variables, and I challenged Jerry to find out how Edwin Hubble made his determination that, how he measured the Cepheid variable. How did they do it back in 1923 versus how they do it now? So I'll turn it over to you, Jerry.
Yeah, so this challenge was given to me earlier today. Okay.
I figured you'd need half an hour or so to figure it out.
Yeah, about a half an hour. So there's the first approach, where you go find direct evidence or documentation on the internet somewhere that says what his technique was and what he did. And I did not find anything the short period of time I've had to look.
Mm-hmm.
So what I had to do, the second way to do it, is just to understand the time period and what equipment they had and what techniques did they have available to them, and the way I would do it back then with those techniques, right? So the techniques are, they had photographic plates. They didn't have CCD imagers. They had microscopes. Okay, they had that type of stuff. They didn't have any electronic measuring device per se. Now, early in the 30s and 40s, when electronics and tubes were coming about, there's an instrument called a densitometer that was developed, an electronic densitometer that was basically used a photomultiplier to measure, and with the light shining through the film, it could measure the density of the film. And then you could scan a photograph or a glass plate and understand the brightness of the object. But I don't believe that was in place in 1923. I think they had to take the photographic plate with a microscope, and I'll talk about some other things that beforehand. But the typical, or the way they would have done it, I think, is they would take a microscope and measure the diameter of the star, because the diameter of the star is proportional to the magnitude. And you see that on star charts today, the way they're drawn. You see that on our images today, that they look typically bigger in diameter, and that's because of the threshold of drawing the pixels on an image, right? You say, okay, pixels of this brightness will show up on the image, and the brighter a star is, the profile is the same. It's a Gaussian shaped profile. It's called a point spread function. But the brighter the star, the light gets spread out even further and further. It gets brighter and brighter until you saturate the CCD image. So that's how it works with film also. The brighter the star, the bigger the diameter of the star. So that would be the way that he probably measured the magnitude of the stars, basically on the diameter of the image through a microscope. Okay.
Mm-hmm.
So I don't think, if he understood, I'm sure they understood that the profile of the brightness of the star was a Gaussian shape because of the optics and the way diffraction works with a circular aperture. That's what it forms a profile like that. So he basically determined the magnitude of the star in M31 based on the diameter through a microscope measurement. I think the other thing I'm curious. I couldn't really find anything with this. I didn't have a lot of time, but how did he know that was a Cepheid variable? How did he know? He had to do time. He had to do several images and do a light curve, right, over time to determine it was variable. And then he had to see that the shape was correct for a Cepheid variable. So I'm wondering if this image that he took, 98 years ago was the last in a series of images that he plotted the brightness and said, that's a Cepheid. And that's when he said variable.
Had to be. Had to be.
So that was, so I had to be a long sequence of images. I don't know how many it would be. It's over, if a Cepheid, what the type one is, like 4 days or something. I'm not sure what the cycle is, but he had to do several cycles, I'm sure. So now you got all the stars in the galaxy, right? How do you know which ones are changing and which ones aren't that you can see? So you have to do some kind of blink comparator, like what when Pluto was discovered.
And Carolyn Shoemaker was using a blink comparator.
Right. So you had to be able to pick up the fact that this star was changing in brightness over that field through a microscope. I don't know how you would do it. I guess he had a microscope and a blink comparator that would switch out images or something. Or I don't know what the mechanism would be, but that's probably how it was done. Mechanical blink comparator that goes between two different plates, and then you can look through a microscope at an area of the star where the star is located and see it. That's the only way I could think of that it would work. So that's the basic technique.
So in comparison, how would we do it today?
Well, one of the things, one of the other interesting things is, I'm wondering, so what David Eicher said was that he calculated the distance as about 1 billion light, 2.5 million light years, right, away is what it is today. But they thought it was like 1 million light years away back then, right?
Mm-hmm.
So I'm wondering if the magnitude was off. So 1 magnitude in brightness is equal to 2.5 times. Okay. Equal to 2. And so, or 2.5 times the distance. Okay. So if he overestimated the brightness by 1 magnitude, that would mean it would be a million, like it'd be 1 million light years instead of 2.5 million light years.
It'd be cutting it in half.
So he basically overestimated the brightness, and it may be because the film that he was using was biased. It was more sensitive to blue instead of red. Film was sensitive back then to blue light, and if the Cepheid was more bluish, then it would make an image that is brighter, I think, and that would cause the distance estimate to be short. I thought that was pretty interesting. So,
well, you remember watching on the short documentary clip that we had, they were talking about how difficult it is to measure distance, and so this is a daunting task,
Right. So if you can calibrate the Cepheid variable, that's what it's for. It's a standard candle, right? So that's the period for the thing determines how bright it is in absolute magnitude. So from that, he should have been able to estimate, okay, this is the period, this is what the absolute magnitude should be based on that absolute magnitude and the size of the star on the plate compared to other stars in the in our galaxy. This is how far away it is, probably. That's how he would have done that. But depending on, he may not have had a very good light curve on the thing, so who knows? We'd have to see some evidence of that. Today we do different techniques, and I'm going to bring up my screen. I've got I'm going to go ahead and bring up my main display because I've got different things running to show you. I don't want to switch back and forth on them. So I found this website just to talk about the basically photographic film technology used in astronomy and what the advantages or disadvantages of them are. And film basically has low quantum efficiency from 1 to 3% basically, which require long exposure times. Today's CCDs are upwards of 90% quantum efficiency at their peak, which is typically near the red, probably. That's correct, Gary? I think it's near the red where the peak quantum efficiency is on CCDs today. It requires long exposure times. You get reciprocity failure, which is a non-linearity. So the brighter the star gets, the smaller. It's not a linear relationship between the size of the star on the emulsion and the brightness. It's non-linear. So now when you try to estimate the size or the brightness of the star, it's not a good measurement when it gets too bright. You got the same thing from color sensitivity. And then today we can digitize plates and measure them with an instrument called a microdensitometer, which is it's basically is a way to do pixel brightness with a piece of film. Do the same kind of thing that we have with our CMOS or CCD cameras. That's just one thing I wanted to talk about. Let me bring up. All right, so I've got an example right here of M67. Okay, this is just a quick example of what I'm talking about for doing measurements today. So if we were to do the technique they used in 1923 to measure brightness, they would basically just measure the diameter of the star. So, for example, let me bring up the other graph window, and I can show you what I'm talking about here. All right. Bring up star profile. So this is a star profile tool that I have in Maxim DL, which shows you the profile of the star. So I'm on this star right here. You can see it's got this bell-shaped point spread function.
Very
now,
smooth looking,
yeah, it's very smooth depending on how many pixels you have and how bright they are. So this one right here, the peak brightness is around 20,000 ADU or counts. All right. Now if I go to this, and you can see the floor is around 2,000, 2,500, something like that. I'm gonna have to increase my aperture. Let me do that. So I'm gonna redo this. And then we've got this star. Okay, so this goes out. If we want to measure the width of this thing, or so how basically the diameter of that star, you would pick a point. Typically it's full width at half maximum is the standard. So you go to the maximum value, which is 20,000 divided by 2, which is 2,000, but it's the difference between the peak and the minimum. So it's actually 20,000 minus about 2,500, or let's say it's 18,000. So you take 18,000 divided by 2 is 9,000. So 9,000, which is about right here, would be the full width at half maximum, basically, which comes out, if you look down there, it's about 3 pixels. Okay, around 3 pixels. Now let's take another star that's a little larger, like this one. Let's see if. All right, that's got a little brighter.
This is infinitely easier than what Hubble would have had to do.
Oh yeah, he had to move around, right?
He didn't have a program where he could just run a cursor over a star and see its brightness. Okay.
Right. So one thing to keep in mind. Okay, I'm going to get to this. So if you measure the full width at half maximum on a brighter star, it comes out to be about the same. All right. So you're wondering, well, what the heck? It's brighter. It's a bigger diameter. Why is it the same pixel distance? And it's because of the way I've got the histogram set, okay? The histogram sets the cutoff point for when it shows this diameter, when it shows the brightness of the star on the pixel, okay? So I can change this cutoff point to make the stars bigger and smaller. Watch. See how they're getting smaller in diameter?
Yeah.
Because I'm changing the histogram. All right. So, and then they get blobbier when I get bigger.
Sure.
All right. So that's the cutoff point. So what you have to do basically to measure brightness in this realm is to sum the value of all the pixels. So the sum of pixels in this star is a lot less than the sum of pixels in this brighter star, you know, in terms of the ADU count. So you basically sum the total ADU counts. Okay. So let me show you what that looks like. That's today. That's how we do it. I'm going to bring up the information window. I already had it up. And show you. I don't think. Oh yeah, I do have. So I'm going to do an aperture measurement, which is going to show me the intensity value. Okay, so right here, the intensity value is going to show us how bright it is. Basically, you have a magnitude calculation for that too. So I'm going to click on this star. And it's got an estimate. Now this hasn't been calibrated. So this is a relative. Let's say it's a magnitude of 13.5 for that star based on this intensity. These are the total number of counts that are within this aperture. Okay, 537,000 counts. All right, now if I go to this other star, which is the other one I went to, it's slightly brighter. It's at 13.0 magnitude, and it's got 805,000 counts. So that's how we measure brightness today. And there's other things involved with the technique to get calibrated measurement, but this is the general technique of how we do it. I've got another photograph here. Since we're talking about galaxies, I just wanted to show this M63. This is a photograph I took back in 2016. And let me bring it up a little bit so you can see the extent of it. So there's my token galaxy photograph for tonight's presentation.
Nice.
M63. I'm not a deep
All
sky
the fire alarm features.
Yeah, I'm not a deep sky photographer per se. I do it when the opportunity arises. I don't go out of my way like you guys do, Cameron and those guys do, to get really excellent photographs of galaxies. When I run across them, I'll take some photographs.
Yeah.
But I don't. Most of the time, I'm more into photometry and astrometry type measurement type things.
Science images.
Science, right?
Mm-hmm. That's right.
So,
well, we will, as we transition between you and John Briggs, I'm going to show Gary Palmer's image of M31 that he just shared with the presenters here. I thought it was definitely worthwhile to show here to the rest of the viewing audience. So let's go there. Gary, are you available to talk a couple of minutes about this image?
Yeah.
There we are. Okay. All right, here we go. There we go. That is a very beautiful image of M31.
That I can promise is just a test image. It was literally an hour's worth of data. So it's 20 times.
Nice test.
Yeah. Nice test.
Yeah. So that's all it is. It's just it had the ASI 2600 camera on there and an L Pro filter.
Beautiful.
Now
Now this line that I see right here, it looks like there's an arrow. Is this
that's
where
the area that star was in.
the Cepheid variable? Okay.
Yeah. I'm just homing in on it now. I've actually got a shot from last year. We took this on one of the star parties last year when we were playing around with some images, and I've locked onto it with this one. So in a little while, I will post the image up, and you can have a look at it.
Yeah, it's
But
beautiful.
I have actually got the star there, so just working on that at the moment.
They say we're going to crash into this galaxy, and I guess if you have to crash into a galaxy, you might as well crash into something as beautiful as this one. So I think it's amazing.
I think over the last 10 years, it's probably this and M33, probably two of the most imaged galaxies. Certainly this time of the year.
Ever. Yeah, I would agree. Okay. All right. That is wonderful. That is wonderful. Okay. So up next is John Briggs. John shared with me a PowerPoint presentation, which I'm going to start up. But John, why don't you come on and say a few words before we get started?
Yeah, no, thank you so much, Scott, for the invitation to come back and see all the friendly faces. I had some work-related travel recently, so I've been a little out of touch, but I had an opportunity to spend some time at Mount Wilson years ago, and of course I love to go back whenever I can, and I'm keen on history. And so given the theme tonight and the opportunity to talk about Edwin Hubble and his literature and just a touch upon his history, and also a personal message, you might say, from one of his proteges that was relayed to me and a group of students years ago. I am passing on from Alan Sandage to the group. So anyway, let it rip, Scott, and I hope people enjoy the PowerPoint. I'll answer any questions at the end if there are any.
Okay. All right. So here we go. We are going here, and
we just want remember to share the sound.
Yes, I got it clicked off, and here we are. Okay. Hold on. Let me stop this for just a moment.
Oh, this is John. Yerkes is an amazing place. And in some ways, that's quite a grandiose title, but you'll see where I go with this, and I hope you enjoy it. But mainly, if we want to talk a little bit about Edwin Hubble. Maybe your mic was on too or something. Yeah, I'm afraid we're not getting any sound. Sorry for the hassle, Scott.
Yeah, I can hear you, John, but I can't hear Scott.
There's a trick to doing this, and we've succeeded before, but It's always tricky.
Yeah, hold on for just a moment. Why don't we have you share it, John?
Let me try. Sorry. Thank you for your patience, everybody.
Yeah.
Let's see now. I'm inexperienced myself doing this, so
just
I'm
go
trying
to
to remember.
share. Something's not right with my sound setup.
Share. Okay. I'm going to try starting the talk.
Say we're seeing your desktop right now.
Good.
Okay.
And let's see. Slideshow from beginning. Hello, this is John Briggs speaking from Magdalena, New Mexico. And tonight I'm going to be talking about Can you hear the talk? Hubble, Mount Wilson, and the literature of cosmology. That's quite a grandiose title, but you'll see where I go with this. I hope you enjoy it. But mainly, if we want to talk a little bit about Edwin Hubble, we go back to Yerkes Observatory, where he was a graduate student in the early 20th century. Yerkes was dedicated in 1897, and I've shown this picture before in this forum, but there's always something else to say about places like Yerkes Observatory and Mount Wilson. Yerkes is an amazing place. And in some ways, aspects of it haven't changed much since Hubble's day. Many students have passed through the institution. Of course, it was founded and owned by University of Chicago, but now a new nonprofit foundation, the Yerkes Future Foundation, is operating it and restoring it for a new role in science education. For his thesis as a graduate student, Hubble used the telescope that was then located in the South Tower at Yerkes. And it's an area I know well because I worked as an engineer also at Yerkes in the 1990s. And in fact, my office was on the first floor where those windows are with what looks like an air conditioner. I didn't have an air conditioner. So this picture must have been taken a little more recently than my time there. But anyway, in Hubble's day, the dome was occupied by a 24-inch reflector that was really quite famous in its day. It had been made by George Ritchie, the famous optician, later responsible for the 60-inch and 100-inch telescopes at Mount Wilson, and many other things at both Yerkes and Mount Wilson. The instrument mounting and tube assembly were built right in the Yerkes Observatory shops. The founding director of Yerkes was George Ellery Hale, and his interest had been especially the sun. And among the other instruments built at Yerkes was the Snow Horizontal Solar Telescope, shown here as it was housed at the observatory. But within really just a handful of years of the dedication of Yerkes Observatory, Hale's attention was being diverted by the wonderful observing conditions in Southern California. And he thus planned an expedition to take the Snow Telescope to the summit of Mount Wilson. And so you see here under construction, the new roll-off shelter for the Snow Telescope on the summit of Mount Wilson. It was the first major instrument that Hale brought to that site. And of course, you can read about it in the Astrophysical Journal, the relatively new journal that Hale had founded with his colleagues, the editors there, Hale, Frost, and the collaborators, William Campbell, Henry Crew, Charles Hastings, many A.A. Michelson, who was the first Nobel Prize winner in physics in the United States, and on, many famous astronomical names among the co-editors of the Astrophysical Journal, which was already up to volume 21 in 1905. Now, if you've never looked at these early issues of Astrophysical Journal, you might think, well, I'm not an astrophysicist, so I probably wouldn't enjoy that very much. I don't know enough about astronomy. But Hale and many people of his era wrote in a very engaging style, including pictures. This may be one of my most favorite pictures in all of Astronomical Journal, in an article published by Hale. What's it entitled? Truck for Hauling Heavy Instruments Up Mount Wilson Trail. This is explaining how the snow telescope and other things were installed during the earliest days of Mount Wilson. And so, of course, nowadays, it's not too likely that you'll see a picture of a horse in the app J, as most astronomers and astrophysicists refer to it. But these older issues, well, I would argue that they are as interesting to read and peruse as any old issue of Sky and Telescope magazine and other things that many of us find very inspirational. After the snow telescope, quickly came the famous 60-inch at Mount Wilson. And of course, a little bit later, the fabulous 100-inch reflecting telescope, the Hooker telescope, named for the donor of the 100-inch mirror blank. Now, though Hale had left Yerkes Observatory behind, it continued strong and especially training many new young students in astronomy and astrophysics. And again, if you turn to an astronomical library, you can read about it. For example, let's consider the early days of Edwin Hubble. As I said, he had been a graduate student at University of Chicago at Yerkes Observatory. And it turns out his PhD thesis was published in volume 4 of the Yerkes Observatory publications. Let's take a look at it. Photographic Investigations of Faint Nebulae by Edwin P. Hubble. And here's the first page. And you know, his thesis is only about 20 pages long, and a lot of his tables describing positions of newly discovered nebulae. I'll just read the very first paragraph to give a sense of what this is about. Photographic Investigations of Faint Nebulae. The study of nebulae is essentially a photographic problem for cameras of wide angle and reflectors of large focal ratio. He meant fast reflectors there. The photographic plate presents a definite and permanent record beside which visual observations lose most of their significance. Perhaps the one field left for the older method is the measurement of sharp nuclei deeply enshrouded in nebulosity. New nebulae are now but rarely seen in the sky, although an hour's exposure made at random with a large reflector has more than an even chance of adding several small faint objects to the rapidly growing list of those already known. About 17,000 have already been cataloged, and the estimates of those within the reach of existing instruments based on the ratio of those previously known to those new in various fields lie around 150,000. And so it goes. Any current astrophotographer would enjoy reading Hubble's thesis and understand it. He was trying to figure out basic things about the nebulae. And in fact, one of the 20 or so pages is simply a reproduction from somebody else's paper. European astronomer Wolf had classified nebulae, and Hubble reproduced the illustration in his thesis. There was still a lot to learn about these things, but this was clearly the direction that Hubble's interests were taking him. Meanwhile, Hale and his colleagues in California had made spectacular progress expanding the facilities at Mount Wilson. As Hubble was finishing his graduate work at Yerkes Observatory, the 100-inch telescope was coming online, and it was ready in 1917. It was clear that astronomers at Mount Wilson wanted young blood like Hubble to come and exploit this amazing achievement of instrumental astronomy. But before we consider some of the things that Hubble became most famous for a little bit later, let's look back in the library. In this case, there's a long run of kind of obscure publication, Annals of Harvard College Observatory. But also with that run, there's something else, the Circulars of Harvard College Observatory. And here we go. Turns out the circular number 173, which was published in 1912, contains a very important paper, something that was very important to Hubble's later progress. The paper is entitled Periods of 25 Variable Stars in the Small Magellanic Cloud. But what we remember it for is it is an account of the discovery of the famous period luminosity relationship, which allowed such an important step out in our so-called cosmic distance ladder. And the first sentence, written by the Harvard College Observatory director Edwin Pickering, reads, "The following statement regarding the periods of 25 variable stars in the Small Magellanic Cloud has been prepared by Miss Leavitt, Henrietta Leavitt." It goes on. It's only 3 pages. And here's the ending page. Arguably the most important thing, those graphs showing that depending upon the absolute brightness of the variable star, there's a dependable relationship for the length of its period. So if you observe a star with a certain period, you can use this relationship to understand what its luminosity is, how strongly it's glowing, and you can compare that to its apparent brightness and then calculate its distance. It's a big deal. Being able to understand the distance to nebulae based upon the periods of variable stars observed in them, which was possible to do given the power of the 100-inch telescope shown here with Hubble at the Newtonian focus, well, it allowed him and his collaborators some very significant revolutionary achievements there in the early 20th century at Mount Wilson. And yet again, delving into an astronomical library, we can jump forward in time to 1931, when Hubble and his collaborator, Humason, published perhaps the paper that they are especially famous for. And here it is, the velocity-distance relation among extragalactic nebulae.
With the help of the Henrietta Leavitt period luminosity relationship, Hubble and his colleague Humason were able to expand the cosmic distance ladder based upon the redshifts of their observed galaxies. Depending upon redshift, they were able to work out how far away the nebulae were, the more distant nebulae. It was an observational recognition of an expanding universe, and it was a very big deal. Now, Hubble, through the years, he was a mentor to a young astronomer shown here, Alan Sandage. And I was very lucky because I worked at Mount Wilson for a little while, observing with the 60-inch telescope. And then later I returned and I assisted with the earliest days of something called CURIA, a summer program, Consortium for Undergraduate Education and Research in Astronomy. And what did we do at CURIA? We reactivated the SNO horizontal telescope from Yerkes Observatory. It was still there at Mount Wilson. In the course of doing this work, I had a chance to meet Alan Sandage himself. It was back in 1990, and the CURIA students, some of them shown here at the SNO telescope spectrograph, and we had an opportunity to hear a special intimate lecture directly from Alan Sandage, who had been something of the protege of the late Edwin Hubble. And the lecture was down in the so-called monastery, shown here in the background, with a number of the early Mount Wilson astronomers, including Albert Einstein visiting in the middle of the group there. And Hubble is actually the fellow seated on the left-hand side with his face turned towards Einstein. Right inside that porch, and in this very room, it's kind of like a living room for the Mount Wilson Monastery, which was the nickname basically for the dormitory and dining facility for astronomers there at Mount Wilson. That's where the CURIA students and I gathered to hear Sandage. And I want to pass on to you what Sandage particularly recommended to us in that intimate lecture. And of course, this here is another historical photo from, I gather, the 1930s when Einstein was visiting Mount Wilson, shown sitting in the same room at the center of the table. And that is Hubble standing right behind Einstein. So this is what Sandage said to us. This is what he recommended. After explaining some basic facts about observational cosmology and the expansion of the universe and such things, Sandage simply said that in his belief, the best way, even to this day, and this was circa 1990, to learn about observational cosmology was to go back in the early literature to Hubble's early papers and read them all, because in Sandage's opinion, Hubble and his approach was very sensible and appropriate and logical and inspirational, and the way to understand how to proceed forward was to have a clear understanding of what had been achieved in the past. So again, he was recommending that students and anybody interested turn their attention to the old libraries, consider the early volumes of Astrophysical Journal in a set like the one shown right here. Or another way to do it is to consider a set like the Brown volumes in the middle of this photograph. Those are collected contributions directly from Mount Wilson Solar Observatory, later renamed simply Mount Wilson Observatory. So while Astrophysical Journal published papers from observatories all over the country and the world, there were specific publication runs like these brown ones here, specific to Mount Wilson. So an even more intense concentration of papers by Hubble and his colleagues there at Mount Wilson. One can find these things and peruse these things, and I only emphasize they are surprisingly readable by all students of astronomy today, but too often they're ignored, and too often astronomical libraries, surprisingly, are being somewhat recklessly discarded by current librarians and astronomers because they feel that once things have been scanned, they're easily accessible. Well, it's true, but there's really something to be said for looking at real books, and that's a long story, but I've run out of time, so I won't go into that, but find these things and check them out. They're wonderful. On the other hand, if it really is inconvenient for you to get direct access to the old journal runs, of course, there are other ways to delve into this, to learn about the history, as Sandage recommended. Look at his own book, The Centennial History of Carnegie Institution of Washington, Volume 1, the Mount Wilson Observatory. Sandage produced this shortly before his death, and it's the rich history of Mount Wilson in a single volume, and it's waiting for you to discover. Thank you very much for your interest and attention.
Wow, that was great.
I hope the sound was okay.
Yeah,
If
it
we
was
set
okay. It
it
was a
up
little,
right,
a little bit low, certainly better than the sound I was broadcasting. So
when we master how to do this, it comes through really well. But
Yeah.
if maybe people cranked up the volume, they could still hear me. I'm glad they could not really see me well right now, but I hope they like the pictures that I had.
it was wonderful. It was wonderful. Also, I really admire you, John. I mean, for your demeanor, the way that you have cared over, historical objects in astronomy, but also the people, the books. I mean, if there's anyone alive today that has really so tenderly curated these things, you're certainly one of the best. So
thank you.
Thank you so much.
Tragic how many things are getting thrown away.
Oh my God.
And so that's a whole other topic, but it's important to remind students and all of us that these things exist and they're really good. And folks have to see them to appreciate them. So it's a fun aspect of the interest to keep in mind.
Thank you so much. Thank you. Okay. All right. So we are running a bit behind, but we've had some great presentations. Up next is Marcello Souza. Professor Marcello Souza is running a program that is the Young Stars of Tomorrow. It is catching on like wildfire down there. He has many students already enrolled in it. And Marcello, why don't you describe it to us and introduce some of the students that are part of this program?
Hi, nice to meet you and all of you here. It's a great pleasure to be here. Thank you, Scott, for the invitation.
Thank you.
Now we are authorized to say who is supporting our project. We are developing the project that Young Stars of Tomorrow will begun. Now, last week, I will show the logo of the project, and we have the support and the financial support from the U.S. consulate General Consulate in Rio de Janeiro. They are supporting our project.
Wonderful.
I will show here. It's the first time that we develop a project here with the support of the United States Consulate here in Rio de Janeiro. And the main axis of the project is the development by students of creative missions of exploration of the moon and beyond. And from this central axis, we will train students in physics, mathematics, and astronomy, in programming for application development, in electronics and robotics, and in the elaboration of 2D and 3D illustration animations. And with this knowledge, students will be motivated to develop creative projects for exploring the moon with the use and development of new technological resources. And during the process, we will identify new talents among the students, and we invite them to join the project development team. This is the main axis of the project. We are planning to visit 40 public schools until the end of the project, and we will involve more than 2,400 students during the 1 year duration. That is the time that you have to develop the project. And we have 40 students involved in the development of the project. All of the 40 students are here. After they make their presentation, I will share some images of what we are doing now with the project. Here is the first school that we visited. Is a rural city place here in our state, in our city here. But later I will share the image. I will introduce now the student, Scott. Here, Robson is here. He is responsible for the logistic part of the project.
Hi, I'm Robson. I'm a physics student, and I'm responsible for organize and plan the young stage of tomorrow's project. And so far, it already carries out activity in 3 schools and 2 different municipalities. The activity will be held in 5 municipalities and thus of the school to inspire many students. And we have here Kezia and Elizabeth and Karen. Okay.
And now, Kezia Barbosa, she is responsible for the part to make the presentations and to talk with the students about astronomy and physics. Kezia. Kezia. Your microphone is mute. Seu microfone está mudo, Kezia.
Are you listening now?
Yes, we hear you.
Yes,
Okay.
now yes.
So I'm Kezia. As Marcelo said, I studied physics on the undergraduation, and now I'm part of the program teaching about astronomy, the principal axis of the project. And I think it's a little important to talk about my little progress in the group as a member of Astronomy Club, because it's why make me so glad to be a part of the program. Because as a member, I have a lot of opportunities. I integrate a small part of a group that visited some centers of scientific and institution of education, institution of science. And for me, it's a big pleasure to be part of this program, because it's my opportunity to share with other students all my experience, all the things that I learned with being a member in Astronomy Club. So this is some images of the projects. And in class, we discuss about some challenges and about how to can send humans on the moon, to the moon, and how can they live there safety. So this project, it's so important in my opinion, because it's a way to find the like a new future generation of scientists. And this is the one of the focus of the project. And that's why I'm so glad to be part of this program. So students receive a little notebook like this that they are writing about the biggest challenges to be need to overcome when we send a mission to the moon. And in the class, we discuss about how to send humans to the moon, how landing on the moon, how can we build a rocket to send the people there, how can I build a base and live there in safety way. We need to discuss about temperature variation, because the condition in space is not like we have here on the Earth. So students study about these topics, and then they need to find a way to make a mission to there, to live and create a base and go to the moon in a safety way. So at this type, with try to find the new talents in this area. And this all that I do in the project. Basically, I talk and I teach about astronomy and all these challenges, and then students are motivated to think about, as they are a really person that think about how to create a mission to the moon. I'm sorry because I'm not fluent in English. I don't know if
Actually, you're doing just fine. You're doing great.
Okay.
You know, so don't worry. Don't worry. Yeah, I think that you're coming across very nice, and you know, we get it. You know, so it's a wonderful challenge, and I'm glad that those of you who decided to come on tonight, you know, are expressing to our community of amateur astronomers, and some are professional astronomers, some are just generally interested in science. So it's great to hear from people from around the world, because this is the global star party. So yes, so that's great. Any
Scott,
other?
we have
Yes.
here more two students.
All right, good.
Developed.
Great. Bring them on.
Isabelle is responsible for the programming to teach students how to make, because we are working with astronomy and new technologies. And Isabelle.
Great.
Hello. Good night. And first of all, thank you for the space for us to show our projects. And sorry for my English, it's terrible. Years without practice. Well, my name is Isabelle. I'm 21 years old, and I am a computer science graduation at UENF University in Campos dos Goitacazes. In the project, I kept the programming part. In my presentation, my lecture, I talk about the history of computing, algorithm, programming language, artificial intelligence, robotics, mechatronics, and bionics, and teaching how to program an application and MIT App Inventor, the sites. I teach students to program mobile apps at the MIT App Inventor. And my experience in the Young Stars of Tomorrow project has been amazing. I got off of my comfort zone, and I'm able to teach the kids what I have learned and also put into practice by making the app. This experience is being sensational. And thank you very much to Professor Marcelo and to everyone who are together in this project, to Robson, Kézia, Caroline. It will be amazing. That's all.
No, it's great.
Okay. And the other student is Caroline, that she is in the high school. And all of the students that are here, they now have a contract supported by the US consulate to work in the project.
Wonderful.
Caroline is the artist. She is passionate also with astronomy and is the artist of the project, because one of the axes of the project is to develop animations. Caroline. Caroline? Você precisa...
Okay. Here she is.
Are you listening?
Yes, I can hear. We can. Podemos ouvir, sim.
Okay. Hello, everyone. Good night. I'm Caroline. I'm 16 years old, and I'm in the high school. And some friends of mine also like astronomy used to call me Astrolink, so I decided to use the name for my scientist holdings and these things. And the Blue School Scrub helped me to do things that I love most, that's art and astronomy. And I took this picture after receiving the awards of this competition, Tomorrow's Stars, of the same club. And now, showing my evolution in my drawings and my animations, I think I can hope to inspire other young people to do what they also love, because I know how difficult it is to show science and physics and mathematics for kids, for people, and these opportunities are unique. So I'm so glad and I'm so happy to be in the projects, to be in the club, and hope to be an inspiration to everyone around me. That's all.
Very good. Very good. Caroline, one of the things I find most fascinating is visualizations about science and especially for astronomy. You know, there are so many perspectives and things that we can't see even with the best instruments, you know, but they can be interpreted through art. And so I certainly encourage you to do all you can to follow in that path. That will be very helpful to young stars in astronomy, and I think that and will carry you far in your life.
They are doing a fantastic job here, Scott. We began last week. Could I share some images of you?
Oh, of course. You've got the stage. You can do anything.
I will share here. And because we are now developing in schools, I have visited 3 schools. Now, this is the image of the school. Here, let me see. I need to leave to. Okay. Here is the first presentation. And thank you, Scott, for the support of the mentor for the project. Thank you very much.
It's an honor for us to participate in all of this, and we'll help in every way that we can. So.
And here, the students, we are in a pandemic period here in Brazil also, and we have many. We need to be careful about the contact between students. Even with these problems, many students are participating. They are participating as volunteers in the project. Here is the first presentation is a school far down from downtown. We are looking for schools that are distant from these big centers. Stephen Hamilton is also supporting. He sent the sunglasses to us to give to the students.
Mm-hmm.
Here, Kezia, Isabelle, Caroline, and we visited 3 schools, and every week we will be visiting 2 schools here in our region. And you have a surprise here, Scott. October 1st, we did the first presentation, and we will do 4 presentations, October 9 and October 12. That is the driving of astronomy now for kids. Then here you see the cars. People participate from their cars. And
I
now,
love this. I love this. This is great, you know.
But you have news. Now have the participation of these characters here during the presentation. This is the first, we did 2 presentations here. We talk about astronomy, and you have the participation of these characters here during the presentation. Because October 12 is the Kids Day here in Brazil. Then we, with the support of the shopping center of our city, we are participating in this project is a driving of astronomy for kids. And is the new we are developing, and every day we have 3 days of activity with 2 sessions every day, because we don't have any opportunity to have more cars, because all the days they had full. They are full with, and 70 cars in each session, 140 cars per day that will show the presentation.
Great.
Thank
Great. How long, Marcello, how long did it take you to develop this program? You've been doing education in astronomy your whole life.
Yes. 30 years.
30
Since
years.
I finished my graduation, I began to participate in an astronomy club in my city. We founded the astronomy club in Niterói, that's other city that's where I born. And then I began to work in a different city, that's campus, 25 years ago. And I'm living here since 1994. And I worked there, and when I moved to the city that I live now, I founded another club of astronomy. That is our group that celebrated 25 years this year of activities.
Oh, that's great.
And I work at a university here in my city. And all of us in this astronomy club are volunteers. And we receive the support from companies and the municipalities, the federal government, the state government, and now the support of the United States.
That's wonderful. That's wonderful.
The consulate of United States. This is the first time that you have a project in our region that is supported by the United States consulate.
Oh, wow.
And you are
Long
going to
overdue.
visit. And as Robson said, we will develop the project in 6 cities of our region. And you have here, receive financial support from the federal government, because the city is where is produced 70% of the Brazilian oil. It's produced here in our region. It's the Middle East of Brazil.
Yes, that's a lot. That's a lot.
But the cities receive royalties, but nowadays we have problems with this, because in the past they received many royalties, but now it's not, will not receive so much as in the past, but even with the money from the royalties, we have many people here that are poor, and is is an interior region. Is like this that say in English, né? A rural region. We have farms here, and the students that live far from downtown. We are doing what's possible here. Thank you, Scott, for the
I think it's
opportunity.
fantastic.
And thank you all the guys here, Robson,
Excellent.
Kézia,
Excelente,
Isabel.
Marcelo.
Obrigado. Thank you. And Caroline, they are doing also a great job here, a great work.
Yeah, I can't wait to go, once this COVID pandemic gets more under control, I would love to return back to Brazil and South America and visit our friends down there, because I think that you do an amazing job, Marcello. I have to admit, Caesar, Maxi, these other people in South America, they are so passionate about astronomy, and they get young people very, very excited about science, technology, engineering. And I think they know that this is very important to their future. And the event that I was at a few years ago with you, Marcello, I was really amazed at how many young people filled your audience to listen to science presentations and to be involved in astronomy. So congratulations on putting together the Young Stars of Astronomy. And I think it's just, I think it's fantastic. So thank you for sharing. Now, by the way, Marcello Souza, along with David Levy, are editors of Skies Up magazine, which you can download. I'll give you the link here, but it's a free magazine, a global magazine. Let's see, here we go. Skies Up. And you can get it. The most recent issue right now is about Saturn, and the new issue coming up will be about dark skies. So, of which I hope to have Marcello back on again to discuss with him hosting a global star party. So it'll be very cool. Great. Thank you very much, you guys. Thank you. Thank you. Okay, so up next is Cesar Brillo. Cesar is, as we all know, is in Buenos Aires, and he is, someone that we all love, and just because of his friendly nature, his knowledge, his passion about telescopes and astronomy, and so I'm going to turn it over to you, Cesar.
Hi, Scott. Hi, everyone. Let me know if you are listen me good.
Yeah, we hear you. The connection's a little slow, but hey, you're all the way around the world, so.
Okay. I'll share my screen because I have a very with very high sync or very bad sync. I don't know what the people say. If it's bad, if it's good. Well, the bad is when you have a lot of turbulence, and this, as today we have the typical thing in springtime that Buenos Aires, we had a warm evening. Now is incoming fresh air from the south. The temperature is again going a little low, little colder than now. Let me center Saturn, and I show you as soon
It's
as
very
possible.
windy tonight, Cesar.
Not here. No,
No?
Really, no. You don't know me in a real situation of wind. Scott really know me in a real situation of wind here in the balcony.
Oh.
Yes. Yes,
Yeah.
Maxi.
He
Once the time
has the nickname
was
of
like
100 mile per hour Caesar. So.
yes, I have my name. Yes. not only in the eclipse of Buenos Aires. Once a time, I remember that we was talking with Scott, Gary, Jerry.
Oh my God.
I remember that I took a picture of 47 Tucanay and another thing in the
Yes.
sky with that condition that was really fun because was horrible condition of wind, really very high.
But he
Let me
still got
share.
images. He still did.
Yeah, okay, I have an image. It was incredible. Let me share the screen.
That's right. Also, the eclipse. The eclipse was very.
The eclipse, yes. Maxi
Oh.
know the wind in the eclipse because they Maxi and his friends had a very low, very near to our situation. You can see the screen with Saturn, a live image?
We can see it.
It's impossible get a better focus. The quality of this Maxutov is amazing. It's amazing. Really, they have an excellent working with the Maxutov lenses because it's the core it's the core of every Maxutov telescope. The lens, we call it in Spanish menisco, but I don't know. It's like a dome in English. I think that maybe Scott, you can tell me.
You're talking about the optical design of the telescope.
Yes, but
yes, it is
you can call it dome or
Dmitry Maxutov comes up with this idea of taking a mirror, a primary mirror that's a sphere. Okay.
Yes, it's amazing.
But when you make a sphere into a mirror, okay, and you form that image, you get something called spherical aberration, which means that the light coming to focus from the edges of the mirror focuses at a different point than the one that's going deeper down in the mirror and coming back up. So you have all these layers of focus, okay, depending on where you are. To fix this, you need a spherical corrector. Okay.
Yes.
The Hubble Space Telescope, when it was launched and put up in space, had spherical aberration. And so one of the ways that they fix this is they put a spherical corrector in front of the sensor. Okay. Suddenly everything's razor sharp, right? Same thing here with the Maxutov telescope. We have a primary mirror, and then Dmitry Maxutov comes up with this corrector that's also spherical. Okay. But light's passing through this clear lens and hitting the primary mirror, and it's correcting out the spherical aberration. On the back side of that corrector, they illuminize a spot, so that becomes the secondary. All right?
Yeah.
So he drills a hole in the primary. The light comes through the corrector, corrects out the spherical aberration. It hits the primary, is gathered up, but before it can come to focus, it hits the secondary and goes back down through the hole, which is the Cassegrain focus. So you have this nice, short, folded reflector system, which is really compact. Okay.
Yes.
So this is the popularity of the Schmidt-Cassegrain design, Maxutov Cassegrain design, or even what's called a classical Cassegrain design, which has no corrector, but to have something in your backyard or on your balcony and be able to get an image like this of Saturn, okay?
And also watch it
You
with
can
your
hold
hand.
in your hand, okay? You could take it on a bus or on an airplane or something. It's very portable.
Yes, and
it's
I
very
love
fun.
that I working with my totally Wi-Fi mount. I use him very simple and very soft to move to center the planet. Later, I'll show you Jupiter, but this is Saturn.
But look at what you can see. On my big screen on my wall here, I can see the forward-facing ring to us. You can actually see the shadow hitting against the planet, the ball of the planet. Occasionally, some cloud features of Saturn on the ball of the planet pop into view, and so what we're seeing is moments of very good seeing in between moments of not so good of seeing. So
yes, mostly it's horrible. But for that,
but what our brain sees, our brain is actually capturing details, and so we can see some details in here, and we kind of ignore the distortion. So that's how our brains work.
Yes.
Right, but a camera can work the same
Yes,
way.
the Cassini division sometimes you can see by a few seconds. Well, this is the principle of the lucky image, or the moments that you choose between the bad moments and the good moments image. This is the how work the system for astronomy. Today I have my images are today really bad. I introduce a friend that is Eric Gonzalez. You know to Eric Scott because he promised you some barbecue in the top of the mountain.
Yes, he did.
His, observatory. and
but I know this is a horrible thing for Argentinians to hear, but I'm vegetarian.
Oh, no problem. We can.
There's no problem.
Make, some vegetables.
Are you kidding me?
Really?
Yeah,
I'm vegetarian.
No, I don't believe you. I don't know why.
Yeah, it's true. But yeah, you can. I eat corn on the barbecue. That's fine.
Okay. The wine is a vegetable. The wine.
Yes, vegetables are fine on the grill. No problem.
Yeah, no problem. Well, Eric is tonight in the historical observatory of San Juan. Tonight is not in the mountain, if not it's in a 100 years old, I think, telescope. But Eric can introduce you, talk about the place where he's now. Well, good night, Eric. How are you?
Hi, Cesar. Really nice to see you again and be here among friends. And yes, as you said, I'm right now just beside my office here in San Juan City. And I have something to show you here. We have
nice office.
It has an interesting window.
Yes.
You can see they were there. Let
wow.
me switch the camera.
Che, no hace frío ahí.
Here we go. Well,
no,
do you remember
have
that,
another sense of the temperature. I know.
Oh, beautiful.
Nice.
Oh, yeah.
That is beautiful.
This is the
I'm really freezing now.
179 millimeter refractor. It's an apochromatic refractor, 100 years old. That was donated by a banker from the city nearby, 200 kilometers south from here. And we use it mainly for outreach. It has never been used to research, obviously. We have many instruments for that here, but this one is our favorite toy over here.
Yeah,
right now it's pointing at Jupiter. Wait a minute, I have to crank this.
Oh, it's a mechanical
there we go.
drive.
We have tracking again.
Wow.
Yeah, it has a regulator there, counterweights here, and it moves. And it's really, really good at keeping the object in the center of the eyepiece.
So that thing spinning on top is a speed governor, I guess, to keep the motor running smooth.
Precisely. I didn't know how did you say that in English?
Yeah,
but
speed
yes,
governor.
that's speed governor. Oh yeah, it's similar to the translation in Spanish.
Huh.
Yes, too small counterweight. If it spins too fast, it opens and activates a little brake. So it regulates to the correct speed. Let me see if it's tracking. Yeah.
This is a big observatory too.
Oh, yes. Okay. Maxi don't laugh about this.
Oh, there's
But
Jupiter.
There's Jupiter. Of course, through my crappy cell phone, it's not much, but I was talking to with Cesar about this. I'm doing mostly outreach in my job, so I just come off from the mountain. We have a CESCO station where we have our research telescopes, mainly the double astrograph that Yale double astrograph that I used to search for variable stars. And there we take visitors, of course. We have a platform with two telescopes, two 10-inch telescopes for people to come and see the sky with us. And I was talking with Cesar about the quality of the image of those two modern, really nice and modern 10-inch telescopes with GPS tracking 50,000 in a modern telescope. And this thing here is really a lot better. The way you can see Jupiter or Saturn or any even bright object or faint object. About when we were talking about the color of the of these objects. I was trying to say through the telescopes at CESCO station, we can see many nebulous galaxies. Of course, Jupiter and Saturn are on about the horizon now. But the color that you get with this thing here is stunning. It's really something else. And you don't get that with a 10-inch catadioptric telescope. This refractor here, yes, it gives you that. So I had a small presentation prepared about historical telescopes here in Argentina. Of course, remembering that it's 150th anniversary of Cordoba Observatory, founded by one president called Sarmiento here, controversial figure, but cool guy in some aspects. Mainly because he kick-started astronomy in Argentina. But well, I had to leave my PC at the office. I have only cell phone connection here, so instead I wanted to show you. What do you think about this dot?
I think it's cool.
The son of that is I never seen that, you know. I never see how it works, how it moves.
We are learning from telescope like San Juan, because in San Miguel Observatory we have one of that telescopes, the Gustav Hayden telescope from Germany, and have the same system for mechanical ascension. It's great, really.
Wow.
Yeah, yes.
John asked to Eric who was the maker of that beautiful scope.
Oh, this one is the everyone knows Carl Zeiss lenses, of course. This one is a stain hair. It was the main competition of Mr. Zeiss.
Excellent. I think the connection with Eric is.
Did we lose Eric's connection?
I think that yes, maybe because he's using the data phones. Because
it's amazing.
Far.
Caesar, you bring on so many great people.
Yes.
It's great. It's good.
Steinhill.
Yeah.
Equatorial telescope. Refractive type. 175 aperture.
Let's see if I pin it. Does that help?
He's online again.
Yes, but maybe he don't have a.
Well, if he's not talking, it will be no principal in the view, I think.
Yeah.
Let me see if I can share it somehow.
Yeah, I know this telescope is amazing. We visited in the eclipse of San Juan. We visited that telescope. It was really great.
Eric, you have to talk.
In a main condition.
Can you hear me again? I'm here. I don't know if you can hear me, but
yes.
Remember that Caesar, he has wind? Well, do you remember that movie Crocodile Dundee where this guy comes with a knife and the other one says, that is not a knife, this is a knife. Well, we have some winds that they call sonda wind. People are kind of proud of it here. Meaning 50, 60 kilometers per hour.
Oh my God.
Every day.
And we are having that right now. I'm inside at home, so the telescope is mostly protected, but the cell phone signal comes and goes.
Eric, I noticed that the observatory slit is very narrow. And so is that because generally you have high winds?
Yes, in here, down from to the city, yes, we have really strong winds, precisely in this time. We are springtime here. October and November, we have this sonda wind that we're starting to have right now. So tomorrow we will have some falling trees right inside the observatory, probably. Well, spot a signal right now. Yes, we tend to have really strong wind here.
So, Eric, I would love to have you back on Global Star Party. Maybe because of the connection, it might be better to make a video, and then you could send that video to me, and then I can have you on live as well as showing the video, so we can get something more high resolution, which I think will work out very well. But the observatory looks beautiful. I mean, it looks like you guys really take care of it. And, the age of this instrument, is, you mentioned, is over 100 years old, right?
Yes, and we still use it to show things to the visitors. We have a 12-inch telescope, but most of the teachers and professors here prefer to use this one. And yes, you can see why. It's really a stunning view with this thing. Okay, let's send the video next time. And probably next time I'm going to be at Cisco Station, 2,300 meters above sea level, where we have the Yale double astrograph. That was a very important telescope from a historical point of view, because many things that we know about galactical dynamics were learned with data from that telescope. Was the main source of proper motions of stars on the southern hemisphere, almost up to the data releases from Gaia. So it's a really interesting instrument. I'm in love with that telescope, and I would love to show it to you.
Oh, that's great.
At the end of this month.
That's great.
Excellent.
Yeah. Beautiful, beautiful. Okay, so...
Eric, disfruta la vista y aprovecha. Enjoy the view.
Yes.
I'm going to point to M57 right now. That is because...
Well, I'm pointing too outside.
Oh, yeah.
Yes, I'm doing live view with the cam, and now in a few minutes I will show. I will do a little tour of deep sky objects from the south.
Okay. Okay. All right.
If you like, I have Jupiter. Few less than 1 minute, I can show you.
Okay. All right. You guys trade off with your live views. That would be great.
Yes. Let me share. Me. It's acceptable.
Oh, it's more than acceptable. It's good.
Mm-hmm. And also you have the great red spot, I think.
Nice.
I think it's
Yeah. I need to don't move, because if I move, like my floor is a deck in the balcony. Yes, I know that I can move everything, but I think that I can take some videos because it's not so bad. But really, you feel proud of this optics, Scott. Really, because
it's always, if you work in this industry and then you see how your telescope works out in the field like that, yeah, it's a good feeling, sure. But the most important part is that they're getting used, they're getting put onto the sky. Caesar, I'll tell you a story. When I used to work for another company, another telescope company, Mead Instruments, sometimes telescopes would come back from large stores and they were returning them because it was so easy to return the telescope. I mean, those of you guys that are out there listening, some people buy telescopes and then they instantly return them because maybe they think they're too hard to use or something, or that's just not for them. But it always made me feel sad to see the telescopes come back, and I knew that they had never even seen one star, not even one. This is their whole purpose of being built, okay, was to see stars and planets and the moon.
You're right. I felt very times the same things with people.
I think so. I think you would. Yeah, but it hit me very hard one time because I saw 20 pallets of telescopes come back from a very large retail store chain, and none of these telescopes had ever seen even one star. And I thought, wow, people don't realize how much hard work goes into making one telescope, even a small toy telescope. It's a lot of work, so
it's so sad. Too sad.
Absolutely.
Yes.
And today,
hi. Hey, Pika.
Hi, Pika.
Officially, Pika's here, so it's the after party.
It's the after party now.
Yeah.
I was going to have a 10-minute break, but okay. So,
today,
so we'll take it to gallery mode here and let people talk. But we haven't let Cameron Gillis give his presentation yet. So.
Oh, yeah, Cameron, sorry.
Right? It's Cameron's turn. So.
About the telescope.
Perfect timing.
The sad story. This is like a opposite of sad stories, that when you begin to astronomy, you will have several scopes. And after just one look through one scope, you will never want to sell that. You just put it on the side for waiting for that time to use that scope. Then you get next one, and maybe that's the same story. You will not sell that. You will have it for that specifically moment.
Right.
And then you have your favorite as a baby. You treat it as your own baby.
It's your own child.
Yes. It has everything that it needs. It has a dust cover. It will be like dusted. It will be fixed and look it after. So I would I would have a thought to think that I will sell one of my scopes because I will have use for them later on.
Yes.
If I'm not using it personally, some kid maybe do that sometime when they come up to me and or I am on the field. They are a little bit not so expensive, so I don't cry blood if they drop it or something. So, but yeah, for me those are like it's like it's one of my elements.
Yes. You know, David Levy, who opens all of our global star parties, he has many telescopes and he has names for every one of his telescopes. He names them, you know.
That's
and
cool.
So he's one of the latest ones that he has. The name of the telescope is Eureka, you know. But he has another telescope called Echo, and he has many, you know, he has 20 telescopes or more that have had names. So it's they're special to him, and he really sees the telescopes as like having personalities, and they're like people. You know, he works with them so much, like you do, Pekka. So, yep.
I have an old story before Cameron jumps in about names for things.
Yes.
I worked for the company Ericsson that makes mobile phones, or used to do all times. And our on mobile phone section, we had our boss and our headquarters in Raleigh, North Carolina.
In Raleigh, yep.
Yep. And when when we have to invent a new phone, he gives the name for the project name for the phone, and all those project names for the new phone was one of his old ex-girlfriend's name. It's like Marianne, Mary, there was Roxette, there was many girl names, and every project has a girl name, and those say that it was his young times girlfriend's names. Okay, Cameron. Thanks, Scott.
And thank you very much, Pekka. Thank you.
All right. Hey, everyone. Hope everyone's doing well. And here we are in Global Star Party 66. Another excellent, on my favorite topic. Yeah, is galaxies. I just love galaxies.
Galaxies, Edwin Hubble, you know.
Can't get enough, with Hubble. And, you know, it's really, there's so much, you know, basically the birth of modern cosmology, right? I mean, just being able to really understand the dimensions of the universe and really have a better picture on where we are. And it's so fascinating, you know, and now kind of bringing that to what we're doing here on the kind of the amateur through professional astronomy is we have the technology to kind of connect all the dots and really get our bearing and kind of internalize and really understand and be more conscious of where we are. I mean, it's kind of like a map, right? I mean, and that's where I, as you know, I'm working on this Camstronomy sky survey, which is kind of like an orientation of you know, there's lots of different star maps, but I really encourage everyone here as we're learning about the science and everything to really go out there and look up, you know, keep on looking up and learn about star hopping and observational and of course imaging to capture your thoughts and
keeping a journal of what you see.
And keeping a journal of what you're seeing, exactly, and then you really start to really enjoy it. It's so let me share my screen. First of all, I'll earlier I was really piqued by Gary's you know, orientation of the variable Cepheid variable in Andromeda, and I was doing some Googling and I looked at an image that I took, and let me just share my screen here. Let's see here. Yeah, well, that's not this one. Don't worry. We're going to go to this one. And okay, here we go. Presentation. Okay, so here is a famous image. This was taken, I got it from the NASA APOD location. And this is actually the plate from Hubble, which you saw earlier. And I just move this out of the way here. And this is a zoomed in section here where you see the variable, and he's put these two hash marks. Kind of, there's a triangle of faint stars here, and it would be this star right here. And I was like, oh, okay, well, you know, for my days of, you know, using an 18-inch Dob and star hopping and doing visual plate solving, I said, okay, let me see if I can identify this pattern of stars here with one of the photographs that I took. So this is a photograph I took in August, around midnight. It was a 10 30-second stack with my C8, and you can see the dust lanes here. And
Yeah.
I was just comparing this image here, which is on a slightly different angle.
What's interesting about the 1923 plate, maybe
Yes.
someone else brought this out, but you see how the word "in" is crossed out. He thought that he found a nova, okay, initially, and then he's going, no, this is variable, and exclamation point, you know. So I believe that Jerry is correct, because he probably had several images of this field. And he noticed that the Cepheid that is so far away, okay, because they're finding Cephids in our own galaxy in the Milky Way, okay, and this is the first time for them to find a Cepheid in another galaxy. So he's looking at this very weak light, and he notices that it's got the pattern of brightness changes that Cephids have, but it's really, really faint. And so at first he thinks it's a nova, and then he realizes, hey, this is variable. So.
Oh yeah, and the fact that, like you say, I mean, for all intents and purposes, you know, when you see stars, you assume they're in our galaxy, right? And,
sure.
And then the fact that he was able to resolve stars that were in another galaxy, that's a feat in itself. And then of course, doing that redshift, you know, the spectrum comparison of the Cepheid variable, and it was like, wow, that must have been just, he, like you said, it fell off his chair. I'm sure he just went,
his
like,
mind
what the
must
heck?
have just been blown right then. Like, holy smokes. Yeah.
Exactly. It's like, and imagine the thoughts, you know, what he was thinking. People are going to think he's a lunatic or whatever, or that he's totally wrong, or like erroneous results.
Sure.
It can't be out for an order of magnitude. It's just fascinating to imagine that moment in time when there was no view that anything was outside of our galaxy, and these were called spiral nebulae. It's amazing. So it was like, okay, well, you know, I was like, hey, this is cool. I love this type of stuff where you kind of rediscover, kind of take that path again with our current stuff. So I took I had this picture that I recently took, and I was like, hey, let me see if I can find it. And I was like, it's kind of in this area. And then I'm pretty good at recognizing patterns. So I found out, if you take a look up here, and I'll have some zoomed in pictures, you'll see this pattern, this string of stars here, okay? Just keep this in your mind. And this is how you can find it yourself, okay? So basically this string of stars with those two stars there, that's this string of stars right here. And I'll show you how I orientated that. So if I blew it out, and this is the same exposure, except, and then this is the frame that you'll see on the next page, where I was able to identify the plate and where it is. So where this yellow arrow is pointing is actually the star. And if I zoom in, this is actually the zoomed in section where you can see, and I want you to pay close attention again to these stars here. That's this string of stars very clearly here. And you can see this pattern here, this pattern here, this pattern here. And I know this for a fact, as you start visually plate solving this, you can start to see, now obviously with my sensor compared to a 100-inch, you know, plate, with photograph, my stars are going to blow out, as you can see, right? I mean, they're quite a bit more blown out, so they're much more sharper images here. But the fact that I'm able to pick out some fainter stars, and guess what?
You are.
I
you
actually
got it.
found.
That's it.
I got it. That's it. So these are there's that triangle
Oh, wait a
of
minute.
stars
Now,
here.
Cameron, this is cell phone astrophotography?
No. This is an ASI 294 uncooled.
Okay, ASI
But to
294.
Molly's point to Maxi, if I had a cool camera, you can imagine this would be really slick, right? I mean, with a cool camera, you can get rid of all this noise.
Okay.
This isn't even cool. Yeah,
I think we can try now. I think I have shot Andromeda right now.
You got shot.
Go for it. No. I encourage everyone I'm sure if you take a look and you do this visual plate solve that I did, you'd be surprised. You'd be able to pick it out. I'm pretty sure, because this is only a 30-second, 10 stacks of 30 seconds, so nothing heavy duty. So I know that a lot of the people watching have better capabilities than that. So yeah, this is so it's very exciting. I mean, this is like rediscovering, and it's really fun. I wanted to share with everyone this kind of little mini journey I took as we were going here. So
for me, this is for me the real, pure, genuine amateur astronomy.
Yes.
Yeah. Thanks, Pekka. I feel it too. It's like just like very crude, but using the technology and using the visual experience, like the star hopping, using the technology, using the visual, all those things together, and then the history too. I mean, bringing it all together.
Yes.
Yeah.
It's
over
really
98 years to now.
Then we are talking about emotions. We are talking about memories, history. That's the whole dinner.
Yes.
Can you imagine if Edwin Hubble was watching this program tonight? Okay.
Yeah.
Exactly.
And what he remembers is him working on the 100-inch, the world's largest telescope. Okay.
Yeah.
And your telescope is an 8-inch, right? So
yes,
he would completely think this was impossible. Okay.
Yes.
And this makes me so happy when somebody just do it like Cameron did.
Yeah.
And do it like amateur astronomer.
It's awesome.
And gets at the same spot and do work for that.
That's it's really it's a real fun with this
10 points
here.
and a parrot bats for you for that.
Oh, thanks.
We have a saying that's it's an old Finnish saying. When somebody do it very well, they got 10 points and parrot patch.
Oh, that's nice. Oh, the parrot hat. Yes, I do remember that in my Nokia training days. Yeah, exactly. Yeah, that's awesome. No, thank you. Thank you so much.
You know, it's interesting right now. Some of the people are chatting with us in the audience, and Aaron Thompson says, "Sweet, thanks, guys. I just found that star in one of my photos.
There you
go.
go.
Clear as
Awesome.
Cameron's, but it's really cool. It is really cool. I mean, you're doing you're reaching into data that you gathered, and you're making it. We're making discoveries right along with Edwin Hubble here. So, it's kind of an unbroken chain, is what it is.
Yeah, connecting all the. Yep, absolutely. And the cool part is when you do, there are, you see also when you understand the kind of the technology and the instrumentation, you say, okay, well, yeah, like look at the star size, right? I mean, it's a lot smaller on his plate, but on the flip side, we have a better signal to noise with our sensor sensitivity, so we can pick up, for example, this dust lane much more pronounced. Like Gary was saying, right? You can see the dust lane very faintly here, kind of like what you'd see probably visually, but here you can see very clear, and also you see a couple of knots. I want to zoom in to this area here. Let's go back to this. So the same area is right up here. So if I zoom in, so you start to. This is JPEG'd already. So
I can see the little trail of stars already.
You look for this trail of stars, and then you go off, and it's up in here somewhere. But it's when you JPEG it, it's you know, without zooming first, then you lose that resolution. But what's interesting is you have a couple of nebulae here that are in the zoomed in picture. If I go, oops, let me just go back out again. Sorry about that. What's going on here? Zoom back out. Yeah. Okay. Yeah. Here we go. So you can see this part here, and there's some knots of nebulosity. So with a higher resolution, you can probably get some pretty neat features of these clusters here. So it's so neat to be able to see that. And again, you know, Hubble figured it was 1 million light years away, but we know now it's 2.5. You know, it's so cool. You know, and the guys in the South Maxi, you guys can see the Large and Small Magellanic Cloud. You can see the Tarantula Nebula, the Eta Carina Nebula. Oh my gosh, you know, those are extragalactic nebulae, right? I mean, it's so cool, right? It's I love it.
Amazing thing is that first of all, I think that we are in an epoch for two kind of astrophotography. There is one side that lays a huge amount of money to just astrophotographing, and they are doing so good pictures. And then we who takes wants just to have that Cameron just picked. And for me personally, the noise doesn't bother me at all, because that should be there, because that's amateur astronomy and astrophotography. Yes. And the noise is one element of the hobby. We just
absolutely. It's like YouTube. It's like this show, this Global Star Party. It's not polished. It's just real. It's this raw nature. It's naturally flowing. It's very down to earth, if you can call it that. You know, or you know, very.
Yeah, you can call it down to earth, because you know we're
staying old.
It's all connected, folks. So
Stone Age time, because I think the amateur astronomy should be like almost baby steps every day, and learning something every day, something new, and be happy.
Yes.
That's the main point. And I love your picture, Cameron. That's so.
Thank you, Pekka.
So neat to see that you make science there by yourself.
That's right.
You try
there
to
is science.
get your science. Exactly.
Yeah, I mean it's you know, I went through the steps, even just putting
you're identifying a star 2.2 million light years away. One star.
Yes. Yeah,
that's amazing.
Yeah.
I mean, you know, you start with this, and like you said, I already captured it here, and who knows what other things, you know. It's, you know,
billions of other things.
Oh yeah. I mean, and then even bring it closer to home. I mean, it's the same as lunar features, for example, right? I mean, you see where. And then even in Mars, where did the Mars rover go, right? Where did we land on the moon, right? Where are the surveyors?
Right.
And kind of orientating where things are, and whenever there's a new discovery or there's a new nova in a galaxy, I love that when that happens. You know, there was some nova a couple years back in Virgo cluster. I forgot which one it was, M67 or one of those, and you could actually see it. You know, that was really cool.
Like M61.
M61. Thank you. Yes. Awesome, Maxi. Thanks. So my memory was partially there. That's good.
The enthusiasm.
Yeah. No, it's really, it's so fun. So yeah, I mean, I also, while I was doing this, I'm not going to go through it, because, you know, we want to save some time, but there's a whole bunch of, I was just kind of looking through my galaxy pictures of the past, And some of the ones that come up is like this one here in the around the Ring Nebula. Some of these galaxies that are in the same field of view as the Ring Nebula, right? Is you have this one here, PGC. It's not even on the charts as far as distance. But then you have this one, IC 1296, and it actually has spiral arms that go off to the side, and it's 256. It's a quarter of a billion light years away, right? I mean, it's just amazing, and it's all in plain sight. You just need the right camera, and a little bit of, and now that gear is becoming, very, very much within reach. Another one I want to, here's a neat one. I just took this recently in August in Pegasus. I love this one. It's a nice, barred sky. I always love barred galaxies.
Look
Beautiful
at the way
bar,
that curls around.
and it just curls around, and I just love. This is one of my favorite galaxies now. And
it's beautiful.
Because when I was a kid,
it's in Pegasus.
Yeah, Pegasus. Yeah, 7479. Yep.
I think I can point from here.
You can get it. You can get it. I'll show you where 7479. If I zoom back out here.
All right, I like this now. We got astronomers in the northern and southern hemisphere working together. And Maxie's going to get a live
right here. It's 7479. It's on the southern part of Pegasus, and it's let's see here. It's let's see what latitude it's. It's only at 38 degrees north. So above the horizon. Sorry, wait a minute. Right ascension declination. So declination is +12. So yeah, you could see it, Maxie. No problem.
It almost looks like it's face on, but you can tell it's a little bit tilted, right?
Yes, that's what's interesting about this. It has this one dominant arm, which comes out here, and then it has this kind of double arm. Actually, if you see the way they're mapping our galaxy, now that they found it's a barred, like what David Eicher was referring to.
Right.
We found out it's a barred, and you can see how. In fact, look at this one. And then look at another one I wanted to show.
So think about how it feels, just how it feels to live in a barred spiral galaxy as we do.
Yeah, the fireworks galaxy in Cygnus is also a barred, but it has a special shape. It has these spiraling arms coming out here, and it has this double arm thing. These are not super awesome pictures, but hey, they're real. And you can get some structure in it,
right?
And so 6946. I think though, Maxie, this might be a little bit tough. So 6946.
I can point it because it's near from Jupiter right now. So it's at the northwest, almost right now. Let me send it. Oh.
Fireworks galaxy. Let's take a look at it.
NGC 7475.
There's a good picture of it from Sky Safari. It is right ascension declination +60. So Maxie, I don't think you can see the fireworks galaxy.
No, I think not.
No, that's that's one of those. But it's this is a really very interesting, very rich galaxy. It's called the fireworks galaxy because how many supernova here? It was like many supernova have been discovered. Yeah, 9 supernova have been discovered in this galaxy.
What?
So
whoa.
Yeah. So it's that's why it's called the fireworks galaxy.
Yeah.
You never know. There might be another.
Busy making new stars, new planets.
You got it. So keep an eye on this one. And then so and there's a bunch of other stuff, but just to wrap up my segment, I'm in. If I go to my sky survey here, of all everything that's highlighted in blue again is what I consider best and brightest, and we've already done the swath of Milky Way, and we ended up in Cepheid actually, which is aptly named for our Cepheid variable. But Cepheid, we ended up on NGC 40 was the last thing. So now we're gonna start to go down. We're gonna go through Lacerta. There's a couple of clusters, and and then we're going to dive into Pegasus and head down here, and I just we're going to end in M15 on a globular cluster, but then we're going to start to do the rest. But I also want to go. I want to follow along with everyone on right ascension and capture some of the stuff here that's low on the horizon, because for me, as you can see, my horizon is really bad. Like, so Maxi, you see all this beautiful stuff like Pisces Australis, and you can see all this stuff probably directly overhead. For me, I have very limited time, and it's kind of mucky to pick out these objects. So for example, the Helix Nebula, you had a beautiful picture of the Helix Nebula. Mine is a piece of junk. It looks really bad, but I got it.
No, you got it. You got it.
I got it.
Wait a minute. How could the Helix be a piece of junk?
No. Okay. I'll show you how bad it looks. Let me just. It's coming. But let me just show you what I got here. So, here's my Helix Nebula.
Something I have to tell everybody that's watching the program too, that astrophotographers are the most critical people on themselves. Okay, on themselves. Yes. But
but this is bad, you guys. Come on. I mean, you're.
No, but you got it. Look,
no, you got it.
You have light pollution. You've got.
It's very low, but you have the shape. You have the center.
And it's probably one exposure, right?
Yeah, that's one exposure. And,
one exposure. Okay.
Yeah.
It's
and
okay.
If I go, let me close this for a second. Where was the? And I think I went back to it at the end of the day too, or end of the night. This one here? No, that's a couple of galaxies. Love galaxies. This is M33. I have to retake my I have to retake my flats. They totally got mixed up, as you can see. It's not very good, but that was M33, and you can see M33, right, Maxi?
Yes, it's a little more up from from Andromeda, but here in the city, I have the light pollution very red, and it's very difficult to capture from here. I have to be in the farm area to maybe taking 4 or 5, maybe more, 6 hours, I think. No, 4 hours, sure.
Nice. That's good. Yeah, this is only like 30 seconds again, and no calibration, nothing. But you can see NGC 604 nebulosity here, which is kind of nice. You see some structure.
Oh yeah.
And you can see the stars. This is what's neat. I mean,
Can you imagine what that nebula looks like from a star nearby? I mean, it's got to be
the shape that
unreal.
They got. Well, I captured a galaxy from here last week, and you can also see the nebulosity and the very shiny nebula that has it. It was let me search it. It's called the collar de perlas, or pearl or jewel. No, I don't know the in English name.
Gem. Well, yeah, and
this is...
and I think I'll. But the main thing is, as you can see, I'm not ashamed of my crude pictures, because part of what I want to encourage is make people feel good about what you're doing, because as Pekka mentioned, what we're able to do now, even crudely, you're getting a lot of information and you can study. There's some really cool stuff when you look at the structure. It's one thing to make a picture look nice and appealing. Honestly, it's kind of like the difference between taking a picture of a landscape and looking at the rock features versus looking at the beauty of the sunset, right? I mean, they're both nice. They're both nice, but you can enjoy and appreciate the features of the object you're looking at without, and then when you do have a good picture of it, you appreciate it even more. So I like to encourage kind of the full range of quality, everything, just to first of all get the image in the first place. I mean, I can't see this visually, like there's no way. I mean, I don't know about anyone here, but have you ever seen anything like as bad as this image
No,
is?
I tried with
Have you ever seen anything
with a
visually
Max
like this? Yeah.
I did some kind of that last year with another telescope, but pictures. But visually, no, it was impossible to see it.
I've seen with my 18-inch, you could see the dominant arms, you could see the texture, you could see these nebulosity. Even with my 8-inch, I can pick out, this for sure. But the overall, including these further ones, I mean, probably Scott, you've seen in a large Dob, you've probably seen these further arms, right?
Yes.
Yeah, that's where dark sky. I mean, that's
and you can see
there's
some
no
of
substitute.
the
There's no
H2
substitute.
regions. You can in
You
real
can,
dark
yeah.
on big scopes.
I've seen this one here and this one here. If I go to Sky Safari, even in my Bortle 6 through Bortle 8 skies, Bortle 6 not bad, but Bortle 8, of course, it gets bad when it goes to the west for me. But if I go to M33 over here, Pinwheel Galaxy, as it's called, zoom in. So you have 604, but if I turn up the and there's globular clusters in M81, of course, or M31. So if I go to settings, go to deep sky. So I have it capped at 13 magnitude. If I go crank it up here to unlimited. So there's some of these other ones that come in, like for example, I can see this one here, NGC 592. Maybe I could see IC 131, but some of these other ones I couldn't. You'd need a larger scope, but the 8-inch, you can pick out some of these guys, not too bad, and you can see this basic spiral structure. It's not bad visually, but yeah, in a dark, this is what's nice. There's a whole range of experiences you can have looking at the same object, whether it's with a small telescope, a medium, with imaging, a smartphone, a large Dob, dark skies with sky conditions as well. There's so many things. So to be able to look at the object in different conditions is also fun. So don't feel bad. Like I obviously don't feel too bad about taking bad pictures, but it's fun. It's fun to share, and it's fun because you can talk about the experience and what you're seeing, and yeah. So thanks everyone. That's my little spiel for
it's great
for Camp Astronomy this week.
Guys, I will come back
great
very soon. I have to change from computer to my phone, so I will be back soon.
Okay, no problem.
Okay,
all right,
good.
All right, Becca. Talk to you soon.
Okay, if you want, I want to share my screen from my live view, if you want.
Yes.
Okay. Do you see?
Yes.
Yes.
Okay.
All right. Now this is using ASI Air Suite, right?
Exactly. The program of the manufacturer, the software.
Right on the PC though, right? You're using the PC.
Exactly. A notebook outside, and I'm connected by AnyDesk to
Ethernet, right? Using the Ethernet.
No, I'm
right?
using Wi-Fi.
Oh, you're using Wi-Fi. Oh, okay. Okay, that's good.
The notebook is connected to a modem, and I'm connected to the modem, so there's no problem. And I'm taking exposures of 10 seconds, and you will see this. But if I go to auto stretch,
oh yeah,
this is 47 to Canon.
Yeah.
Oh yeah, that's awesome. And you know that I was biting my tongue when we were talking about globular clusters. I agree with what you said earlier, Scott. there's no globular cluster that's the same. They're all so beautiful
Oh,
to
they're
look
all
at.
the
They're so
beautiful
so unique.
treasures, you know?
Yeah, they're treasures. Yeah,
Yeah.
yeah,
Yeah.
yeah. I love it because the
Somebody said
density
it
of the
early in
gold-
the program. It looks like somebody took a handful of diamonds and just
Yeah.
poured it out like in a pile, you know?
Yes.
Exactly.
That's a globular cluster, you know, and I've always felt, you know, when I first started doing amateur astronomy, they thought that globular clusters are somehow the leftovers of a galaxy, you know, and that they were like in this, and they are. They're in a halo.
I think they couldn't be a galaxy.
Yeah, that's right. That's right.
It's almost to be a galaxy, but they couldn't get to there. So
Yeah.
You know what blows
But
me
now
away about
they have
them?
lots of
Yeah.
new ideas about globular star clusters that maybe they are very old galaxies, you know?
Yes.
So because
You
they're
know-
some of the oldest stars, they predate the milk. Yeah, our globular clusters predate the Milky Way, you know? So
Oh wow.
how is
I
that?
did- oh.
Okay.
Whoa.
So
Yes.
yeah.
Oh, that's really cool. Well, you know, whenever I look at this, Scott, I imagine the center of that. I mean, what's amazing, you look at this and it's such a high density. You're seeing a
Yeah.
continuum of photons.
The
you know,
heat
and yet
the radiation.
There's huge
Yeah.
gaps between them. If you were actually in the middle of the globular cluster,
Hmm.
there, you know, it's going to be like bright stars. I mean, you're not gonna. It's not. There's still huge empty space between them, even though it looks like a solid mass. It's amazing. You know,
Yes.
it's as dense
Yes.
as they are. Yeah, I think
So-
they said they would look like basically, you know, I guess like double stars. You might have some. It would look like it might be bright enough, right? I mean, what do they say, Scott? I mean, if you were in the middle of a globular cluster,
Yeah.
would it be like daylight, or would just be like lots of super bright Venuses?
I think it would be like lots of super bright stars. I don't think it would be like daylight.
Yeah.
But you have to realize, let's take M13 for example. Okay.
Yeah.
And the old model that I have, and I have to probably update this model, but the old model was that it had about 500,000 stars. Okay, which is a lot of stars. Okay.
Yeah.
But if you
Yeah.
took each star, and you can imagine how, I mean, if you were up next to a star, even like the size of the sun, it's so huge, right? But let's shrink it down to the size of a pea, okay, that you could hold in your hand. To build
Yes.
your model, okay, using peas as stars,
Okay.
you have to get 500,000 peas, okay?
Yeah.
Make them
Yeah.
into a ball, but they're all separated by 1 mile.
Guys, I come back.
Oh wow.
They're separated by 1 mile, so you can't even see one pea to the other pea, okay, of how far away it is, okay?
That's a good analogy.
Right?
Yeah, that's a good
And
analogy.
then if
yes.
we kind of shrunk that thing down somehow and cut it in half, okay, let's just cut it in half. You could place it right over Antarctica. That's how big it would be, okay?
Wow. Wow. Oh my
So,
gosh.
If you had a
Wow.
spacecraft, you could fly right through it. You probably wouldn't even graze one of the stars. I mean, it's just, you know, they're still so far apart that.
That is super cool. That is a great. That's an awesome analogy. Yeah. You know, it will be cool to kind of have some of those videos made. You know, somebody make something like that.
Yeah.
To kind of
right.
give people some scale. You know, I love
Make
those.
something
like,
you could
remember-
probably kind of deal with, maybe just grains of sand or something. I don't know how big it
Yeah,
would be then.
it's so. Oh, that is so cool. I like that
Like
analogy.
still
though.
cover a
That's good one.
city or something. So
Yeah.
so huge.
Yeah. Oh, it looks like Pekka is sharing.
Yeah, wait, I have
the
to.
moon, or that's his moon.
I
picture.
have.
Yeah,
I
that's his
have.
moon picture.
Wait.
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 Yeah, no
Hey,
problem, no
Pekka.
problem. Yeah, we're hey, Pekka, good to see you. Oh, good to see you here.
Wait. I take if
Yeah.
I find where I take off my sharing.
Yeah.
I'm sharing now, or
You only see your.
Okay.
When you speak, we only see your
moon.
That you're highlighted, but we don't see the moon anymore.
Let's see, how do I get back there? Because this is mobile. First try with mobile phone.
Okay, I'm back. I thought
All right, Maxi.
that my
Maxi is here
scope
now.
push my
All right.
computer and goes to the ground, but no.
Oh, is it still set up? Are you?
It's still set
I
up.
saw you were in you were doing some slewing. Great.
Yeah. Let me share the screen again.
I love that. I want to get set up now. What are you using for your configuration? You have your 8-inch or 10-inch, or what was it? The Newtonian,
8
right?
inches f4.
F4,
Comma
beautiful.
corrector.
This is beautiful.
For
Yeah.
an f4 and the camera.
What mount?
MEQ6.
MEQ6, and then the you're using an auto guiding. What are you doing? How are you doing that?
Right now, I'm using Cartousiel to the EQ mode. This program is connected to the mount.
ASCOM, right?
It works with ASCOM exactly.
Yeah.
And I'm guiding with PhD2 and
but what
EQ.
scope are you using as a guider? How do you do
no, a finder 9 per 50.
But you have a guide scope in there, right? Or sorry, guide camera, right?
I'm using a guide camera. It's a QHY5 mono.
Yeah,
that's why
I need to get something like that because I want to get my guiding calibrated.
Well, they're very cheap. There's
no reason why I shouldn't have it. Yeah, I'm very slow, Maxi. It takes me a while. As you can see, it's taking me some time, but I'm really enjoying putting it all and tweaking everything. But when I get it, I'm gonna get it really. But this is good stuff. I think I'm realizing that I'm gonna need to have an auto guider.
Yes, to do more exposure,
to do longer
you'll need
exposures. Yeah,
exactly.
Yeah.
So I pointed to another. Well, this is the picture that I was taking, but now is going to be this.
Oh, the Tarantula Nebula. It's beautiful.
Oh yeah.
And that is that the jewel box down there?
No, the jewel box is in no, it's in the Southern Cross.
Too far. Okay.
Besides of the star Mimosa, I think. And now it's impossible. It's very to the south. It's here.
Okay.
It's very
so I'm way up. Okay. So now Tarantula, that cluster then is inside the Large Magellanic Cloud, right?
Exactly.
Yes.
Mm-hmm.
Beautiful.
And let's do a picture of more time. Maybe I don't know, 60 seconds. And
while you're doing that, let's go to Cartousiel and let's see your frame. How does it frame on the Cartousiel? I think you have the image. You have the image circle, right, on it?
Exactly. Where I'm pointed.
You can probably put in a. You're using the circles for your eyepiece circles, right?
Yes, I didn't configure it to do the field of view of the camera.
Yes,
it's like
that is really cool. Then you can actually really get it accurate, right?
Well, I can do this. I share all the screen and open Stellarium, and there I have it with the square of the sensor.
Okay, cool.
So I think it's going to be better, but
the main reason why is it gives a sense on the scale, because when I see this is like I see it like I know what it is, but I want to see it in relation, because the Tarantula Nebula is huge, right?
Mm-hmm.
It's like almost spanning half of the Magellanic Cloud, right? The Large Magellanic Cloud. It's quite large. I have to take a look at that though.
Well, let's put out this. And now the center.
Okay, so it's not as big as I thought. It's still huge. Okay.
Yes, that is the field of view that I having right now. You know, it's huge, very huge.
Yes. Yeah.
And I'm having. Are you seeing Stellarium?
I see it, and I see the red box and the highlighted box animated.
Exactly.
Yeah. Yes.
And this is the place.
Yes. Okay. Cool. Because I don't have the same, or I am not familiar with the southern hemisphere, of course, as far as what's in the sky. So I don't really have a good sense on the relative locations of everything and sizes. So this really helps. Oh, that's
exactly.
beautiful. I like that cluster. Oh, that's really nice.
There's a lot of star clusters. A lot.
Oh.
Cameron, you and me will be lost in.
Totally, Pekka. You were
in
right.
Argentina.
We need Maxi to give. Yeah.
We couldn't navigate on the southern part.
No, I agree.
Not even with the stars.
Not even with, yeah, it would be like, that feeling though is a very neat feeling. I remember when I was first learning my way around the stars, when I didn't know anything.
To find in northern skies is really tough, but
yes, but do you remember that, Pekka, when you first were looking and learning about the constellations, and it was like, you didn't know any. That's the way we're going to feel, and we haven't had that feeling probably since we were kids, right? I mean,
right.
And so when we go down to the southern hemisphere, we'll be like kids.
Yeah, we couldn't find home.
It'll be like, wow, we don't know anything. This is,
I got that feeling when I got to Portal 3 skies. It took me like 10-20 seconds to begin to navigate, and we're looking for the constellations because there were so many stars.
Yeah.
That I got totally lost.
Wow.
An overwhelmment of the beauty of the sky, because at home I can see probably like magnitude 3 stars.
Yes.
Magnitude 2, and to be able to see up to 6. And the multiply was like 1,000 or 10,000 more stars.
Yes.
So
I had that. I haven't had that experience except one time I had something close to that. I was in close to to a Soyuz in Canada, in British Columbia, called a place called Peachland, near a Soyuz, right in the middle there, and that's where Jack Newton, I think, has his observatory.
Yeah, I've been there to his observatory.
I always wanted to go. You have? Oh, Scott, that's so cool. He seems like such a nice guy, and he has a bed and breakfast thing going. And I was like, I really want to do that, and it's so close to me relatively. And anyhow, I haven't done it yet, but I remember driving through there one time, and I remember it was the same experience, Pekka, that you're saying. I saw the Milky Way rising over the horizon, and but all the stars, it was so bright, the stars, that I couldn't see the constellations anymore. All I could just see is just stars everywhere.
Bunch of stars.
Yeah, just stars. Yeah.
That's something that it makes the stomach feel like upside down, and you feel like dizzy. You are really like a little bit afraid also. The whole emotion came instantly, because you are a little bit unsure and you are lost.
Here is a 3 minutes picture.
Yes. Oh
wow.
Yeah, nice.
Wow, Maxi.
You start to see the nebulosity surrounded, and
but is yours a color camera or is it a monochrome?
No, it's a color camera.
Okay. So is this like a grayscale image of it, or is this actually a color image?
color image. This is
It
simulating.
should be more colorful than that, right?
Perhaps, maybe.
Is that 294 MC or?
533.
Oh, okay, 533. Is that so good? My
It looks
gosh.
good. Yeah.
Yeah.
Really
No,
good.
I already said and put auto, and in this case, it goes okay. This is NGC 2100. This is this cluster.
Okay, that's
right
oh
there.
yeah, beautiful.
Wow.
I like that one.
NGC.
It's like
2000.
city map with light pollution from International Space Station.
Actually, that cluster, it almost looks like a loose globular cluster. There are some clusters that look like that, that are really nice and dense.
Let's
Yeah,
see if
another
we
one-
can go to this. I don't know if we can find it. It will be there. So
I love M11, the wild duck cluster. I really like that one. Oh, yes, here.
I think is this NGC. Let's see. Rotate. It's very near from there. So
Oh, that's
I
cool.
hope-
You can see it's doing. Yeah.
I hope. No. Let's stop and put it at 30 seconds. Then, if you want, let's
You know
go
what,
to.
Maxi? I think you probably they're excellent images, but there might be something where you've set it to be all gray, because there should be some color.
No, remember this is pointed to the south, and I have light pollution.
Oh.
Here.
Okay. Okay.
So
it
maybe
changes
it's
it,
that.
Yeah. Yeah.
Okay, there it is. Look at this area. Look at this.
Oh wow.
Oh, I love these things. Yeah.
Let's-
spin the velocity like this.
Let's
Oh,
do it at
some
more
structure.
time.
Yeah.
Search stars, start
This is all
guiding,
live. This is so
and
fun.
the stop and do 3 minutes. Now, I think I know. Oh, this is very, very good.
You become
You
very
know,
good at this, Maxi. That's awesome. And this is all new equipment. You're doing great. This is so cool. Nice. It's so
I also-
nice. I like this live driving. This is really cool.
it's a little tour from the Great
Yeah.
Magellanic Cloud.
Oh, yeah, this is so nice.
And then, if you want, well, there are too many places to watch, but if you want, we can go to some galaxies that we have.
Yeah. Let's see here.
Well, I showed later 47 Tucanae, then we went to Tarantula Nebula, and now we can go maybe this Phoenix, and here's Eridanus. This place is full of galaxies, a lot. And
Whoa.
this is one what I took a couple of days ago, but the floods there was very bad, and I couldn't work very good. But
Oh, you know what? Can you do the sculpture galaxy? NVC
yes, I can.
253.
I can point it. I can. Let's stop
Okay.
when finish this. I will do to sculpture galaxy. If you
Oh,
want.
thanks. Yeah, I'm just looking at what I have that's just above the horizon.
Can you guys think that?
Nice that you can use Maxi can help you see further south. So cool.
Yeah, this is great.
Yeah.
This is so
And you
fun.
think that all this software, like Stellarium, Cartesian Seed, everything is free for us, and for fun 100 years ago,
No.
they didn't have nothing.
No, and also the D2 guiding program software.
Yeah.
It helps really a lot, and it's free. You know, I had to. I when you no I don't know how to say when the guys that create these programs, we had to give it a lot of things, you know, because
I know.
they
They've
helps
done a lot.
a lot.
Yes, I agree. Yeah, it's
okay. Let's see how it goes. This. Yeah. Oh, okay. Oh. Oh man, look at this.
Yeah.
This is at 100%
3 minutes.
zoom.
Yeah, beautiful.
This is
fun.
all the image. No. Oh.
Oh wow, you got some other reflection up there too.
Mm-hmm.
Look at that. You know, and that's this is what's so cool, because it's like EAA, you know, as well. Like you're able to share this. We are looking through the same eyepiece as you, and it's like we're looking through a very high and large telescope. You know, and it's still visual, but it's, you know, it's not the, you know, it's a different experience obviously than looking through the eyepiece. I love that too, but just to be able to do this is just wonderful. And in the future, you know, if you do have an opportunity to look through a larger telescope and you look through those, it just makes you appreciate it that much more. It is nice to be able to see this.
Here's
What a great
Sculpture
journey.
Galaxy. So
cool.
It's in the other side. Let's see if we can go.
Let's say, is there something in between? Where are you pointing right now? Let me just see what.
Well, I was to the south, and now I'm going to the west, but very up.
I see
almost
that.
at the zenith.
Okay, let me see here.
We are in the hyperspace. Chewie is sleeping right now.
Oh, I know what I want you to do. I know.
Oh, there it is. Oh, it's almost there.
Okay,
stop very near, but it's in the other side, more to the east, moving the mount. With this camera and this scope, helps you to give more field of view and stop. Okay, I think it's almost centered. So let's do 30 seconds. Now, this place is amazing. I had to come back again to this place and do some pictures. Oh, the spring skies here are amazing. Well, every year.
Nice.
Every time of the year, all the sky. Okay, so let's see what we got. 2, 1. Oh, man.
All right. Yeah. Oh, it looks like, yeah, it's you see, this is what's interesting, even with the star trails, right?
Yeah. Yes.
You pick up the galaxy. So that's amazing. You can still get the structure. And so basically there was a little correction in the last part. So you just have to redo it. Yeah.
Right now it's going to be okay, I think.
Oh, that's gorgeous.
And there it is.
Oh.
It has a little star trail.
Sculptor. That's Sculptor Galaxy, right?
Sculptor Galaxy. Oh, I love it. Yeah, I love that.
Yeah, the lattice work of that, those dust lanes and everything is just so elegant. You know?
Yeah. Oh.
This galaxy helps to, you can see with binoculars.
I have another favorite.
Let's do 3 minutes again. Pika, you, I think he's in office.
Yeah.
And
Okay. Can I, Maxi?
Yes.
This is so awesome. Can I? Let's look at. Oh, that's so nice. Okay, I have another favor. if you're okay.
No, yeah, no problem.
I'd like you to go to NGC. What is it? Give me a second here. 1365 in Fornax. This is a part of the
Yes,
Fornax
I was from the Great Magellanic Cloud. I want to go to be there, but
yeah, let's go there. Let's go there.
It's in the other side. Let's do some
1365
star points. Weights.
Okay.
Do you want to see 3 minutes or we go to there?
Yeah, 3 minutes. So let's get a nice, good view of that, so we can look at the structure and that in the Svalbard Galaxy. You bet.
Cameron feels like
you're saving all this, right?
What? I only one picture. When this take the picture, I can save it, but this is only one. I am not taking pictures tonight. I only did, I think, 40 cents to Canada to practice.
Okay.
But
no, that's okay. We have it on video, so that this is nice. This is yeah. Oh.
You know, I love the core of the
Yes.
galaxy. It's very yellow.
Yes.
Let's
look
do
at
it.
that. Yeah, zoom right in. Yeah, that's nice. You can see the knots of nebulosity and the dark nebulosity. Just really love that. Wow. Yeah.
And also the kind of the galaxies that they are very near, or near of the galaxy from the perspective, but they're very, very far. And no, this galaxy, I love it. So.
Yeah. Oh, wow.
Well, we have 40 seconds. I hope the guiding was okay. Oh no, it's terrible. Oh, it's like a earthquake.
Oh, it must. How far above the horizon is it?
No, it's very up right now.
Yeah. Okay.
It's
yeah, it's far up. Yeah.
No, from one out. Here. It's very up.
Oh yeah. Okay. Yep. Yeah, I thought so.
Okay, let's see how it goes.
Okay. Oh, good. You have round stars, and you even have them showing some diffraction spikes. It's nice, and they're very nice defined. This is a beauty.
That's so good. So good, Maxi.
I like it. Nice, Maxi. This is beautiful.
This is almost at 50. This is 50% of the zoom area.
Yeah. Wow.
And
that's that's a single 30-second, or sorry, 3 minutes, right? It's one 3-minute exposure.
Exactly. And you can see here there is another galaxy very far away.
Yeah.
Oh, I love that. Yeah.
And here's another one.
Yes.
Yes. Yes.
And
yeah,
I think that they are a lot.
Oh yeah, they're everywhere. Really, every little faint
what's neat
smudge that you see is a galaxy.
You got this granddaddy galaxy, right? This big guy.
That's the close one.
But he's just close by, and those other ones that are so small probably are really huge too.
Absolutely huge. Yeah.
Yeah.
Okay. Do you want to be NGC 3065?
Yeah, 1365. It's another beautiful bar. I got to see a bar.
First of all, I want to be to Andromeda Star, to be, if I can be there. So
cool.
A pointed star. And
okay. Yeah.
To see if the mount it's okay. So here's the star, and we are almost there. So let's do 10 seconds.
You're just doing a plate solve to realign the mount, right?
Exactly.
Yeah, that's smart.
Okay, here's the star.
Wow.
Beautiful.
Reminds me of Star Wars.
Now let's put it 5 seconds and the crochet. Oh. To the west, you're going to be up, and the east going to be down. So
We will never learn those navigation patterns.
Oh, sorry.
And to remember to the slew speed. I sometimes don't remember to put it on the one speed one. It's 9, and then I'm way off, and it takes half an hour to find the star again.
Mm-hmm. It's difficult.
Yeah.
So I want to be.
So the software should be implemented when you have a crosshair, so it's automatically made. The software makes the slewing control and speed automatically to 1 or 2. When you get the circle, when you take the setting circle, then the slewing speed goes automatically to 1.
Yeah.
So you don't make a mistake and lose the star when you have found it.
Exactly.
Actually, Scott, do you know why we still need to use a separate auto guiding camera when we can just do a zoom in on an existing camera image?
You mean to guide on the same chip
On
that
the same
you're imaging
chip,
on?
yeah, exactly, yeah.
You know, SBIG made a camera that actually had 2 sensors in it. It was in one unit.
Yeah.
One that auto-guided and one that imaged. But I believe that you can do that. When I discussed it with Meade Instruments when we were building imaging cameras as an idea, they said, well, you know, you can't clock out the chip fast enough to, you know, then acquire an image on another pixel and move the scope, you know, because you'd have to like stair step, okay? So you have to switch to a guiding, okay, make a guide, make a correction, take an image, you know. And on those early days, the cameras are still pretty, I mean, noisy compared to today's standards, okay?
And
this is the mid 90s, okay? So we were using Kodak chips and Texas Instruments CCD chips is what we were doing. So we, you know, and CMOS back in those days was nowhere near the performance of a CCD. Now
they were very expensive, right?
Yeah, now it's different. Okay, so it may be possible. I mean, I'm not an electronics engineer, but it may be possible to fence in like a guide star, okay, and make that part of the CMOS chip behave differently than the rest of the CMOS chip. Okay, so that's something that would
some DSL
investigation.
I think right. I think you hit it earlier, Scott, when you're talking. It has to do with processing. So if you're using all the processing for gathering the image, as opposed to running it at a different rate, like it's kind of like it's probably like taking a planetary image with a planetary camera with high frame rate and a nebula with low frame rate.
Yeah, and
at the same
that's how
time.
it was first. That's how SBIG first did it. Okay, and I think it was called the. It was either the ST7 or the ST8 camera that did this.
Some DSLRs have tracking already. Nikon has, and I think Canon has also a tracking for stars. So they have like 5 up to 10 seconds tracking.
Yeah, that's cool. No, I think it's going to be in the future pretty close to Pekka if they already have it with the camera.
Yeah, DSLR cameras. The sensor.
The chip must be fast enough.
Yeah, but the cost is similar.
Yes. Yeah, right. Yeah, exactly. Yeah, that's an important thing.
Yeah.
Are you prepared, Cameron?
I am prepared. I see something already with my faint eyes. I can see something in the middle of the screen, and I can't wait to see. Can't wait to see your auto stretch and do your exposure here.
Let's see how. I think it's there, but yep, it's in there.
Oh yes, beautiful. Oh yeah, zoom in. Isn't that a beautiful galaxy?
Yeah, that is the one with the.
That's so nice.
That's a real spiral right there.
That is my favorite. When I saw this as a kid, flipping through the library books, and this is in Fornax.
In Fornax, yes.
Fornax,
right on the boundary. Yeah, and there's if you look around that, it is a Fornax cluster of galaxies, very close.
Yes,
if you have a wider field, there's lots of good stuff, lots of juicy stuff.
Those are the extremists.
Yeah,
extreme spiral galaxies.
But this look, zoom right in and take a 3-minute of this because this has camera. When it comes to galaxy, I lose my politeness.
I never heard like this. I never heard you like this, and it's amazing. No,
you. This is definitely my passion.
Cameron is like young children in Christmas
galaxies. Yeah,
give it to me.
But here's the thing: as you're doing this, I'm just really appreciating. I don't like to just move on to the next picture, right? I really am enjoying the structure and looking at it, and we're not even perfecting it and making it like a astrophoto directly. Look at this. There's some other galaxies in there. Oh, that's so nice. And some of those
you must remember that to think how far they are.
Yes. Yes.
The distance and what kind of travel and voyage those photons has done.
Yes.
That's long time.
Here the guiding is okay. We are only in 15. It's okay in this to get a good picture. So we have 18 seconds. 80 seconds. Sorry.
Now zoom in a little bit if you could, just a bit more, because I want to see that central part. This is what's really cool about this galaxy. See that? There's a dark lane that goes right through the core. You see that? And it goes right on an angle. That is so cool.
It's like it's abrasing with the arms surrounded. It's amazing.
I mean, just think about the forces and the fabric of the universe that creates that type of structure, right? That makes that, and I think it was talked earlier in the Global Star Party many hours ago about two galaxies colliding. You'd never even know, right? I mean,
well, here we have to able to see the antenna galaxy. They are colliding. But right now is near in Virgo and the Corpus. I think very near from the Sombrero Galaxy.
Yes.
And I want to try with this equipment to capture it.
Oh yeah, that would be beautiful. And I guess that would be for your winter time, right? Which is summer here, or spring, fall. I guess fall your time, right? Is that right?
Exactly. Yes. Well, here's the galaxy.
Oh, yes. Oh, yeah,
more
look at that.
sharpened because there are 3 minutes, and also maybe the dithering is working, and that's why it has this sharpened area. But let's see.
This is really nice.
If we can. No, it's very.
I think you can zoom in. Press the plus sign. No, after you've done that, press the plus sign on the histogram. Yeah, just press that.
Ah,
See?
yes.
That will make it. You can do some more finer adjustment. Yeah, there you go. Oh yeah, yeah, beautiful. Then you can get the right contrast. Yeah, play with that. Oh, it's just so nice. Look at how far those spiral arms extend too. Look at that. Yeah, way out there.
Yeah.
It's so
Look at the
beautiful.
way that one dust link goes right across the top of the central bulge in the.
Yes.
Just all the way
like
across.
some 3 stars.
Yeah. It must be some.
A lot of stars.
Yeah.
Yeah. It's a real string of
the core of the galaxy. It's just weird to me that the core of the galaxy has that obscuring dust lane going across. Is it another arm that's mostly just dark nebulosity or dark dust going across?
Yes, it's like I think this galaxy is like a ninja weapon, or some kind of that, because
morning star, yeah,
some kind of 2 blades and the part of when you handle it, and it's amazing. It's very rare. It's like a Klingon galaxy or something like that. I don't know. From Star Trek.
Yes. Oh wow.
And
I'm just looking around for other.
Well, if you want, I can go to this area, but there's a lot of this kind of galaxies that maybe if I center this, it's going to be good. Because I love more this kind of galaxy, like a sculpture, but maybe you can go to this area.
Guys, I think I have to jump off because I have some things to do. But have a nice evening. Or is it night already for you?
Oh, you bet, Pekka. Absolutely.
Yeah,
you too, man.
I have a early morning.
No problem, man.
Yeah, and let's see next Global Star Party. I try to pick up something to show, but I would tell you I have a project I want to maybe do for my observatory this week is to find an Earth globe with light inside. So I will remove the foot of it and hang it in the middle of my living room, and because I can make my living room totally black, so the kids can see that way what's around Earth globe. So I hang it like a lamp from the ceiling in the middle of the room, from the height also. So it's like on the outside. So that's a small planetary inside so they can understand a little bit more.
Wow! Look at all these galaxies.
Yeah, that's nice. Good work. Okay, guys.
Pekka, take care.
Okay, Pekka.
Take care.
Thank you very much.
Okay.
Hey,
bye-bye.
Pekka.
Bye.
Thanks a lot.
Bye.
Take care, man. Yeah.
Bye.
Cheers.
So these galaxies, they are some kind of cluster galaxy in Fornax. They are maybe almost, let me see, yes, 62 million light years from us, almost around the corner.
Oh, awesome. Oh, I just love it.
I'm
Yeah, look at
taking
that.
a picture of 2 minutes, but I don't know. The guiding is really upset. I don't know what's happening. I don't know if the windy is giving me troubles or I don't know.
Is it? Oh, you know what? Yeah, it's almost pointing overhead now, right?
Mm-hmm. It's
So
almost
maybe
at the
because
zenith.
of the balance. One thing I found out in the
Oh yeah.
is that
You're not loaded. It may not be
you're
loaded.
not loaded. Exactly. It causes some play in your deck. You're right. Your right
Probably.
ascension might be okay because you know, you can adjust that, but you're especially if you're flipping it up, depending on how your guide scope is, and also because you're not loading it equally, it's floating, right? Your declination is floating.
Mm-hmm. Yeah.
Is that right? That's right, Scott?
Yeah.
Yeah.
Yeah, because you can imagine, okay, you're kind of like balancing it all at the, so it presses on that side of the gear and that side of the gear, and you needed to have all kind of preloaded on one side.
Well, it looks like it gets the focus. So I don't know. I had to see it, but well,
it is in fact aiming straight up. Okay,
Mhm.
This is tough on a mount, and you know, you might do something to add some weight so it's always loaded on one side all the time. You know.
Yeah. No, I think it's difficult. They focus too. I don't know. Sometimes when I point to another places, I realized that I had to focus again. I don't know why. I think the sky looks like a lens, and I don't know. It happened the last days with.
Okay. Sorry, I have one. I have one. You must do this. This will be the last one. Is that okay, Maxi?
Yes, yes. No,
okay.
Tell me.
I was wondering. Okay, 1300, NGC 1300.
Oh, that's very difficult. It's
it?
very, because even how much exposure that you get, it doesn't matter. It's more, how I can say it. Well, first of all, let's do this. Let's stop and parking. And that galaxy is very difficult to capture because you have to get a lot, but really a lot of hours of information to get info.
Actually, no. It says it's if I go here,
magnitude, I don't know, 8 or something like that. But
yes, actually magnitude 10.4. So it's not super bright, but you should be able to get it. I think based on what I saw earlier, I think you're going to get it, and it will look beautiful.
Yes, it's near from sculpture.
Yes.
Also, I had to get focus. So first of all, let's go to. Oh, wait. Spark, and we'll go. Okay, so with Alpha Eridanus, this is Achernar star, rotate. So the meridian flip is good, but sometimes doesn't help too much. Do you remember, Cameron, how we see more earlier the two clouds?
Oh yeah, exactly.
And look at how it goes now.
Oh, you have it on both sides of the meridian. Oh, that's tricky.
Excellent. So let's do it. A 2 seconds picture, and No, it's focus. I think. Yes, it looks like focus.
Yeah, it looks focused.
Mm-hmm. Well, okay, so it's almost probably there, so it's okay. And now let's go to NGC 300. I think it's this. Yes. Telescope rotate. Here's a lot of galaxies, but okay, I think we are there.
I really appreciate this, Maxi. This is so cool. You know, this is the best. I mean, this is what it's all about. I mean, to be able to go north and south. What is your latitude?
My latitude is 34.
Minus
34
34.
south.
Minus
34
34.
south.
And
I think
60
Scott, you're
west.
60 west, and Scott, you're about 34 north, right?
Yeah, that's right.
I'm 47 north. So I'm quite a bit further up, and then I think Pekka, he's like 60 something. So it's but that's really cool, you know, northern south. Now we can really comb the skies. But this 1300, oh, I can't wait to see this.
I come back in a minute. I will see outside in a moment, but I will still sharing the screen.
Okay, I already see something. This is cool. Yeah. Yeah, this is great. I think after this, Scott, sorry, I've been dragging this out again, but we'll probably let Maxi stay all night doing this, and then probably wrap it up, eh? What do you think?
Yeah, I mean, it's been great, very inspiring. Global Star Party. I'm still feeling the energy from it, really, you know, and thinking about, you know, Edwin Hubble, all those nearly 100 years ago, finding the Cepheid Nebula or Cepheid Variable in the so-called Andromeda Nebula, and you know, and I can just really just imagine how excited he was when he found this. You know, it was like it was like finding this beautiful diamond in the rough. You know, and
oh yeah.
Yeah, because now, and I'm sure he felt it at the time. I'm sure he felt that, you know, this will be something I'll be remembered for, you know, throughout history, and that's true. This is what he's known for. You know.
Yes.
He changed humanity's understanding of the cosmos in one night.
Yep. Oh, absolutely, and like you said, I'm sure he was very well aware of the significance.
Yeah.
Yeah.
Well, here's a kind of nebulosity. Here's the core.
Yes.
I think it's more spiral. You know?
Yes. Oh yeah, you can see. Yeah.
See if you can go into the histogram and go zoom it in.
Yes.
And then see if you can bring bring that out like that. And then to the right.
Now you can see it.
To the right, bring the one on the right further
Which
out.
galaxy is this?
NGC
1300.
1500. Okay.
No,
1300.
300.
1300. Yeah.
NGC 300 or 1300?
No, 300.
300. Okay.
300.
No. Yeah, we want 1300.
Oh, so I pointed to another place, I think.
Okay. Yeah. Okay. No, we have to see 1300. Sorry.
This is where I'm pointing.
That's 300. Yeah, that's not the one. Sorry.
Oh, no.
It's nice. It's a beautiful galaxy. And you can see some good structure, but go to 1300. 1300.
Okay. Let's see.
And let's make sure. Let's see where it is compared to now. Hopefully, it's not too far away. But by the NGC number, it's 1,000 off.
NGC.
So.
Oh, here. It's
Yeah.
Right now. Oh, it's more to the north. I have to come back. No, wait. Let's see. So let's park again the scope. Is in Eridanos also.
Yes. Yeah, Eridanus has a huge amount. I that's actually a big gap because the weather for me is getting bad, Maxi and Scott. For up here in Seattle, it's been storming, and Eridanus is coming up, and so there's tons of galaxies in there, and I still haven't done my observations in that constellation yet, complete. So I'm hoping that that I get a chunk of time to capture both visual and imaging observations in the next winter here. Takes me a little longer compared to the summer. Yeah. Oh, yeah.
We have in the summer the Orion Nebula, or the Orion constellation, of course, the Pleiades, and this is how we see it. Here's Andromeda right now.
I know, it's so cool seeing it upside, inverted is probably a better way to say it compared to where we see it and you're so used to seeing it like that. So the Orion Nebula is in the upper part of Orion for you. That's so neat.
Upside down. Oh, what happened?
Yes. I try to avoid that now because out of respect. I think you have a lot of good stuff that worthy of the right side up.
Okay, so here's Canopus. Here's another bright star-like Sirius.
Oh yeah, that's very bright. Yeah, it's the second brightest star, right?
I think it. And they always be together in the summer. You were able to see this, and when you pointed directly, you went to the Great Magellanic Cloud. If you point to
that's cool.
These two stars.
That's nice. That helps me with orientation. Oh, that's really cool. So basically, you want to go in the summertime, like we're right now. For you, this is perfect time to see the Magellanic Clouds.
Yes, it's more in the summer because they are very high.
Right now, they're really high, right?
Right now, yes, they are in the maximum position, but it's very late right now.
Oh, that's true. Yeah. So it's nicer to see it earlier when they're rising, right? As they're coming up. Yes.
Okay, so I think we are in NGC 130 and 3,000. No, sorry. No, I say I don't know.
1300 or 1,300. Yeah, 1300. Yeah,
exactly.
Let's do it that way. 1300. Yeah.
The numbers goes
now. What it's doing right now is those are the stars for plate solving, right?
The guiding.
The guiding.
Well, the guiding what it's doing is pointing a star and also doing a multiple star tracking. So the guide helps to get less errors.
Yes.
In the guiding.
Yeah.
So well, I think it's go okay right now. It's almost at the limits. It's going to be below of this 90. So let's see. Oh, there it is.
Oh, yeah. Now this is a beautiful galaxy. This is another of my favorite bars. Oh my gosh. See, this is This is more like you have the bar, a perfect bar in the middle, and then you have those, instead of extending out like the other galaxy, that going straight out, these arms wrap right around really tightly. Oh, there's another galaxy there too. Why not? Yeah.
Nice.
Look at that.
You,
oh, yeah.
You
this
are
one
able
here,
to
if
see
you-
this.
Yeah, I know. When I see it, it's just a mush. It's just, for me, it's what is it? If I go to, let me just tell you how far it's off the horizon here. Let's go horizon. Oh my gosh, yeah. So if I go, let's here. Yeah, actually, you know what? It's interesting. I should be able to see it. It's about it rises to about 20 degrees off the horizon for me, which you'd think would be good, but it doesn't show very well. I haven't actually. Now that I mention it, let me take a look if I even observed it, because I think I tried to observe it one time. Let me just take a look here. Show observations.
I never heard you so excited, Cameron.
Well, you know the reason why.
He's like a kid in the celestial.
Yes.
Oh yeah. No, the reason why first of all, I love galaxies, but this particular one, if you Google this one, it's a very famous galaxy image, with really lots of nebulosity in the arms that are arcing around, and then a very distinct bar across. So this image you have is just beautiful. It does a good justice, but it's interesting to contrast this one to the earlier bars, that galaxy, where the arms go straight out, right? They kind of go. So it's
Yes,
like you
it's
say,
very
this is another,
sharp
yeah,
arms.
very sharp arms. And if you take a longer exposure, so I highly when you have time, Maxi, it would be great if you get these two bar galaxies. Try to get some nice images of those, like long exposures. They're just gorgeous. They're just beautiful. And yeah, thank you so much. It's really nice to see.
Let's see what we get now. It's 10 seconds of 3 minutes.
Okay.
And I'm
great.
cooling the camera at minus 10 degrees.
Okay.
Yes. Here is at 100%. This is the full size.
Okay. Yeah, it's a smaller one, tighter. But let's do the zoom in on the histogram again, and let's play with the levels. Oops. Yeah. So bring that one there, and then the one on the right, bring that to the right more, actually.
So
just to see. Oh no, that one. Okay.
No.
What I
right,
learned is
to the left.
Yeah, that's good. Yeah, like that. What it will do is that will help with your signal to noise. You see, so if you zoom in to the upper arm, you can start to see some knots of nebulosity, right? In that.
Yeah.
Here. On the upper arm there, exactly. See those nebulae? Isn't that cool? And then the bottom one too, you can see a little bit of nebulosity.
Oh, you mean so like right there on the curve where the hook is?
Yeah. Right where the hook is, exactly. Yeah, there you go. See?
Yeah.
You can see some knots of nebulosity. Isn't that cool? Wow.
Oh, that's cool.
This is beautiful.
It's amazing.
Yeah, I love this.
Incredible.
Giant Orion Nebula after giant Orion Nebula. You know.
Exactly. Ah, beautiful. Thanks, Matthew.
Well,
now I can go to sleep and feel really satisfied.
All right. I think Scott's turning into a pumpkin here. So
yeah, I know. I think thanks a lot, Scott.
Do they use that expression in Argentina that you're going to turn into a pumpkin? Do you even know?
A pumpkin is
the orange-colored fruit that grows on a vine. you know, it grows on the ground. And during Halloween, children decorate these pumpkins.
Unas, sí, una calabaza.
Yes.
Yes, yes.
So we say if it's very late, okay, that you're going to turn into a pumpkin because of the story of Cinderella, okay?
Yes.
Has this big pumpkin carrot, okay?
Has
and the
past
mice.
midnight. Has past midnight. But
Right.
the spell is over.
Because it's so late.
Yeah, the magic is worn off.
To conclude, if you want, let's, of course.
Okay, let's do one conclusion.
This is the strawberry of the ice cream.
Come on. Exactly. Yeah, this is the one. Okay, this is a great conclusion. Yes. Oh, it's already up. Yeah, it's late enough for you guys. Oh, look at that. Oh man, look at that. See, it is a color camera. Beautiful. Look at that. Oh, wow. How long is this?
30 seconds.
Yeah, that's all you need. And you know, when you zoom in, there's two parts of the nebula. There's lots of parts that I really like. But zoom in and go down a little bit. I just love that very defined that part, that reflection right there. That I love that on the lower part. This is awesome. And then this one here that comes in front, that nebula that has the three little holes in it. Yeah, that's one that you see that protrudes in front of it. That's awesome. You can get a 3D kind of perspective, right?
Exactly.
It's like, oh, gee, I love that. Of course, the whole nebula is beautiful. And then if you take a longer exposure, all that texture that's kind of going out to the further, if you have a wider field, you start to see that fabric even further. Oh man, yeah, this is beautiful.
Well, besides of this is the Running Man Nebula, but in the field of view is possible to see it. But the entire nebula of M42 goes okay here in all the square.
Okay, Maxi, I have another request. Okay, I want you to take the horse head, please. The horse head.
The horse head. Okay.
Yeah.
So.
Yes. And that's, by the way, Maxi, that's my goal. Before the end of this year.
I took pictures of that.
Yes. I have never seen it. I've never taken my own picture with my own eyes. I am thrilled.
It's very difficult. Very difficult.
Yes, it is.
Mm-hmm. Yes. Well, I see 434. I think this. Yes.
Yeah, right beside the Flame Nebula. Just look there. Yeah, what's interesting is the Flame Nebula is very easy actually. It's quite bright, even visually. Mm-hmm. But then right beside, of course, the horse head is really elusive.
Yes, I think we are there. So let's do. In this case, I think we have to do more exposure.
Yeah, let's just do one right off the bat. Yeah, no, I agree with you. That's
with 2 minutes, it will be okay.
Yeah. And then we have to. Sorry, Scott. Yeah. Oh, Horsehead Nebula. Okay. Oh, this is a beautiful picture of the Orion. Yeah, it never disappoints. I'm really excited. So I should be able to get something like this.
Yes, probably.
Excited.
You have them almost the same field of view with your camera.
Yes. Yeah. I'm looking forward to that.
You know, and also I love how the colors are more distributed in these pictures. And like I say, I have no glow anywhere. There's nothing.
Yeah, I mean, and you're not. This is just a single picture. You're not doing any flats or darks or calibration frames, right?
No, I mean, no, absolutely. I have to do flats because at some place I have some vignetting, but
this is not stacking though, right? Are you stacking any flats? No.
Yes, I do maybe 20 flats only. with
But
the same temp.
But this image here, like are you
No.
putting in a master?
I didn't configure anything. This is only the picture that comes from the sensor, and that's it.
That's great.
Okay, let's see in the Horsehead Nebula. I hope. Oh, I didn't watch the guide. No, the guide is okay.
Looks good.
So
looks good.
there you go.
There it is. I'm satisfied. That is gorgeous. Look at that. Oh man, there it is.
Let's.
Yep.
Oh, that's the horse head. Yeah.
There's the horse head. Oh yes, and you have the other IC 434 or something like that. The other one to the left.
So you know who discovered the horse head? It was a female
Woman.
astronomer.
Yes.
Wilhelmina Fleming.
Yes, the one that you've named the award for, right?
Yeah. I didn't make the award.
Yes.
It's the Astronomical League did.
Astronomical League, yeah. That is. She was an incredible woman.
Yeah,
I mean,
unbelievable,
yeah.
Unbelievable opposition too that she had to deal with. You know.
Yeah.
So
I think that's so cool. I mean,
persevered.
That is a very good. How can you say it? Milestone to have your name attached to discovering the horse head. Wow, that's really cool. Beautiful.
It's more
well,
noising, but
I'm so happy we can see it. It's like it is so cool. This is what it's about. This is what we were talking about earlier with Pekka. Just to be able to see it, you know, this is really cool.
And well, here's what I did a couple of days ago. Horsehead Nebula, and this is the stacking and processing picture.
Oh yeah. Oh, that's beautiful. And
Yeah,
you know what I
that's
love about that? You know, this is a perfect example, and the way you have the orientation of the diffraction spikes, right? The way you frame
Yes,
this.
I love to put it very
you did really nice.
That's pretty.
Yeah, really pretty. Maxi Filaris. Yeah.
It'd make a
Very
nice
good.
Christmas card, you know.
That exactly. That is gorgeous. Anyone will appreciate that.
Also, I did this galaxy, Collar de Perlas, and this I think is this.
And are you using like a deep stack? Oh yeah, this is a cool one.
Sorry, but this is they are. Yeah,
oh,
Actually has a lot of pictures.
Oh, zoom in.
Yeah, look at this.
Look at that. Oh, I like this.
That looks really sharp.
Oh, especially those. Oh, wow.
You know, this galaxy reminds me. I don't know if you. I'm a very fan of Star Wars.
Oh yeah, right. Sure.
This galaxy reminds me a starship that has the Mon Calamari Chrysler.
Yeah. That's the big Admiral Akbar was in. Right?
Exactly, it's a trap.
Yeah, the big Corsair or the big battleship or whatever. Yeah, the main ship. Yeah, exactly. Yeah. Oh,
I
man.
also look at the tiny galaxies that
Of course.
surround.
Yes, let's look at them. Oh man, they're so nice. Yeah. Oh, I love that. That's really nice, Maxi. Look at that.
Yeah.
Which one is this one? What's the name of it?
This is NGC 55, I think.
55. Okay. Which constellation?
Also Sculptor, I think, because it's very near from the Sculptor galaxy. I think NGC 55. Let's see. Yeah. Yes, in the Sculptor galaxy. At 7 million light years from distance from us.
Oh, beautiful. Yeah, it's another one of those. I'm just looking. It's too far south for me. Yeah, but that's okay. It's so nice to see. Oh, that's beautiful. Thanks, Maxi.
And also, what I did the Omega Nebula, but I didn't like the process. What? No.
Oh yeah, these are beautiful. Yeah, this is
this is not unstretched, but I didn't like it how we see it, so I didn't finish the process and everything. So
really nice.
I think it's all. I have to grab
It's
the
not
equipment
moving
again.
anymore. I think we have to let him go to bed. Sorry. Yeah. Thank you, Scott.
What do I look like, a zombie or something here?
You kind of spaced out.
You know,
there,
yeah.
If I have, if I no, if I would not go to work tomorrow,
yeah,
it's okay.
No problem, right? You
No
just keep
problem.
going.
Yeah.
Yeah.
Right on, Maxi.
I
man,
will
you're
wait
on a roll.
my fiance with mates and everything. It's no problem.
No problem.
But no, I have to work tomorrow.
Oh yeah.
Almost.
Oh,
you got to sell computers, right?
Yep.
Yes, the selling is very hard in this
Yeah.
season. Yes, but that we have to still on it.
Yeah, of course.
This was really great. Thank you so much. That was really
It
fun.
was good. Maxi, thank you so much. Thank you.
Thank you.
Cameron, all of you that watched our program today that are still watching, thank you very much. We'll be back, of course, next Tuesday with another Global Star Party. Make sure that you watch the International Observe the Moon Night event on the 9th, okay, which is coming up this weekend. And, it's going to be a lot of fun. Vivian White has some amazing presenters that are coming on from all over the world. So I think it's going to be very cool. And what else can I say? I love this this Global Star Party. It was fun. And it's great to have all of you here. Yeah. So you guys have a great night. And until next time, keep looking up. So
you bet.
Yeah.
Awesome.
Okay, guys. See you.
Cheers.
And let's find my outros here.
Okay.
Here we go. Here we go. And here we go. Good night, you guys.
Cool.
Thank you.
Good night.
You bet. Good night.
Hi, this is Dave Eicher. This coming week marks 98 years since Edwin Hubble discovered the nature of galaxies and the cosmic distance scale. To celebrate, join me for a special talk on galaxies this week on Tuesday night, October 5th, on the Global Star Party, brought to you by Scott Roberts and Explore Scientific. I'll see you there. Happy stargazing.
Hi friends, Vivian White here from the NASA Night Sky Network, and I just want to invite you all to join us for the Global Moon Party happening October 9th from 3 p.m. on, that's Pacific time, 6 p.m. Eastern time. We are going to have such a blast. We have great folks from the International Observe the Moon Night joining us. We have NASA friends from the Visualization Studio and moon treks and all over the place. We have Icelandic poets to talk about the moon, presenting new work that they're doing. Space agencies from around the world will join us, and we hope you will too. Please get the word out. Let everyone you know who loves the moon know that we are kicking off the International Observe the Moon Night this October 9th. See you there.
Hi everyone, this is Terry Mann, and I'm the Secretary of the Astronomical League and the co-host of Astronomical League Live. We have a special event coming up on October 15th at 7 p.m. Eastern Daylight Time. We're going to have a kind of Halloween party online. We have quite a few speakers. The first one is one of our regulars, one of our favorites, David Levy, and he will be doing celestial incantations. Next up, we'll have Mary Stewart Adams, Passing Between the Worlds Under October Skies. We've also got Astro Bob, Black Holes Where Matter Goes to Die, and Molly Wakeling, Spooky Nebula of the Night, and John Goss, the Master of Lunacy, and we do expect that name to stick. Barbara Harris, Algol, the Demon Star. Myself, Aurora, Soul of the Night. And we've got Carol Orge, the president of the Astronomical League. We're going to put a wizard hat on him and let him work his magic. So please let me personally invite you to join us October 15th, 7 p.m. Eastern Daylight Time, right here. We hope to see you.
Why do we chase this thing? Jumping from one continent to the next, just to bathe for a moment in the absence of light? Who are we? What are we searching for?
T.S. Eliot wrote, "We shall not cease from exploration, and the end of all our exploring will be to arrive where we started and know the place for the first time."
One of the qualities of seeing an eclipse is it makes you understand that every given thing is in a particular patterned relation with every other thing.
It gives me a sense of scale, gives me a sense of where I fit into the universe.
It is art, it's poetry, it's this kind of experience of going and seeing totality in which what feels merely metaphorical is suddenly experiential encounter.
Immediately afterwards, you have that overwhelming desire to see another one. That's the moment an eclipse chaser is born.
These are folks who are running all over the world for this event that lasts all of 2 or 3 minutes. Who are these people?
It's unique each time. And therefore that freshness, even if we've seen it over and over again, oh my gosh, it has the potential to re-inspire us.
A total eclipse of the sun doesn't just unfold in the heavens. It transforms the minds and hearts of those who experience it firsthand. The same is true of journeys to the most remote regions of our planet. Whether we're standing on a mountain peak or in a stark polar landscape, we can't help but reflect on our place within the larger scheme of things.